as you can see, Olivier is with me today. The both of us are going to be the MC for this day. And we are going to host some speakers to speak about sustainable software engineering. How are you, Olivier?
I'm great, thank you. Thank you. Nice to be here. And so today we will be joined by Suze and Nathan, who will be managing the video feed behind the screen. And there'll also be Sherry and Emric. So Sherry and Emric speak English, French, and Danish. And they'll be monitoring the chat on the different platforms. So feel free to ask questions there. And they will just follow them to us. So today, as Maud mentioned, we're going to talk about sustainable software engineering. So 4 hours of conferences with one topic, which is sustainability. 2 languages, French and English, 11 amazing speakers will be delivering 10 talks, and we are broadcasting on 4 different channels. So you're on the English track, and we'll be talking about web, machine learning, cloud, SRE, and plenty of amazing things.
Exactly. And also, I couldn't start this conference without speaking very briefly about the code of conduct. So we want everyone to have a very nice experience, everyone to feel welcome and respected throughout this conference. So feel free to have a look on the conference website, greenconf.io, to have a look at the whole code of conduct. Basically, we're just asking that everyone is nice to each other. And that's it. Thank you. And I will just continue by speaking about some companies, some people who really helped us do this. And so we have Microsoft, DevApps.be, DevDay, Hack in the Boots, ESUG-FR, the Microsoft user group Lille, PyLadies Paris, and Sense of Tech. So all these groups helped us to organize the event, make sure we have a website, make sure we do some nice communication so everyone is aware about the event. So thank you so much for this.
Yeah, and this is the first conference organized by DevCon Galaxy, and we hope like next time there will be like way more partners. Just a brief word about the Azure Hero program. So this is a new program we launched a few months ago. If you have any question, feel free to reach out to Sherry. She's in the chat and she knows everything about it. But basically, it's a program where you can collect badges. And so this one is the learner badge. So if you want to get this one for the conference, just scan the QR code. It's only available today. And you will get a first badge. Or if you want to another conference before, maybe it's the second one. One last thing, yeah, we are going to do a raffle during this conference. So we will see this slide between the talks. So just go on the link aka.ms/greenconf raffle. We'll do the raffle, I think it's in 2 days mode, right? On the 2nd of October. And there will be a Fair Fund 3 to win for the lucky one of you. So just go and play.
And lastly, we'd really love it if you could participate with us and share your appreciation for the talks. So we have 6 talks on the English track. There's also 5 talks on the French track. Feel free to write a little comment if you like any of the information that the speaker gave. Also ask them some questions. We have planned some Q&A session after each talk. So each talk we have 5 minutes dedicated to replying to any questions you might have. You can share them during the talk at any time. We have Sherry and Henrique who are in the chat and they are moderating all of your questions. They are sending to the speakers anything you want. So feel free to ask and say hello. You can tell us also where you come from. It would be really great. I know we have people coming from different continents, different countries today, and we really appreciate it. We also have a Twitter account, DevCon Galaxy, which we are going to monitor throughout the day. And we have a hashtag GreenConf. So feel free to let us know what you think at any time.
Yeah, and share with us where you come from on the chat.
Sorry?
I said people share with us where you come from on the chat. I'd be curious to see where people are from.
And now I think we're ready for the first talk. So the first talk is a bit special. It's going to be a little bit different from all of the other talks. As a first speaker, we have Asim. So Asim is a speaker from Microsoft. He's the Green Cloud Advocacy Lead at Microsoft, actually, and he's going to speak about sustainable software engineering and building carbon-efficient applications. So I was saying it's a bit special for this talk because this talk is going to be broadcasted at the same time on the English track and on the French track, meaning that for this we had to record the talk. So Asim is not live during this conference here, but he's live on Twitter and he's waiting for your questions. So any questions you have for Asim, feel free to ask him in Twitter and just use the hashtag GreenConf, or you can ask him directly at his Twitter handle, Jawash. And thank you. Oh, also, I have a live comment from the chat saying that we have attendees from Kazakhstan, France, the Netherlands, Germany, Austria, Ghana, Italy, Singapore, and Egypt. Wow, there is so much. It was really hard to say. Great. If there's anyone coming from another country, let us know. And we're really happy to have all of you here. So without further ado, let's jump into Asim's talk.
Welcome to this presentation on sustainable software engineering. And if you've never heard of sustainable software engineering, that's fine. Not many people have. It's a very, very new discipline. And this lecture is going to give you kind of a really good overview of what it means and kind of what it entails. My name is Asim Hussain. You can find me on Twitter as Joik. In fact, you can find me as Joik pretty much on every single platform out there. My blog is asim.dev. My website is asim.dev. And I'm what's called a Green Cloud Advocacy Lead at Microsoft, or even the Green Developer Relations Lead at Microsoft. That's kind of my role. I'm going to hopefully explain what that means and kind of what that entails as well during this presentation. But first, picture my son. This is my son, Micah. There's something about this picture that makes me think he loves his daddy. Now, before he was born, a friend of mine, he's about 2 years old now. Before he was born, a friend of mine gave me some great advice, which was, Asim, take the nappy changes. Take the nappy changes. My wife was breastfeeding, or planning to breastfeed, and he said, well, she's going to have that quality time with him breastfeeding. All the relatives and friends are going to be over, so they're going to be kind of playing with him and holding him, and you're not going to have that quality time with your son, so offer to take the nappy changes. I thought it was great advice. And so I took the advice, and I took the nappy changes. And I told my wife, I said to my wife, actually, I'll take the nappy changes. She was very, very happy about this fact, that everything was great. But then a few days later, she turned around and she said, actually, I've decided we're going to use cloth nappies, not disposable nappies, cloth nappies. Now, we thought we were a pretty green family. We recycled, we did a few other things, not much else, but we did what we thought you had to do. Now I realize we need to do so much more. But we thought we did what we needed to do, and we thought cloth nappies was kind of a good step in the right direction, and it is. But the thing to understand about cloth nappies, a disposable nappy, you just poop in a nappy and you throw it away. And a cloth nappy these days, if you've never seen one before, they're actually a lot more advanced than what you might imagine. They're not just a piece of cloth. They kind of have an elastic band. They have bamboo inserts, but you do have to deal with poop quite a lot. You get very, very used. He poops 8 times a day. You get very, very used to dealing with poop. And I'm not bothered about poop at all in the slightest now. I've been in meetings sometimes. I've been Teams meetings or video conferences, and people will be like, Asim, what's that on your face? I'll be like, don't worry about it. It's just poop. I get very, very used to dealing with poop. But then I had an epiphany a few months after he was born, and I realized kind of how come I was happy to deal with poop 8 times a day for the environment, and yet I'd never ever asked once in any technical meeting, in any Scrum meeting, in any architectural discussion, any tech meeting of any nature at all, I had never held up my hand and asked, well, what's the greener solution? I was willing to deal with poop 8 times a day, but in my work and in my industry, I had never once asked the question, well, how can I do my job greener? And that led me on a long, long journey, which eventually means I start my full-time job at Microsoft to both figure out how to build green applications in the cloud, and also even just figure out what does it even mean to be a green application, because it turns out not everybody agrees. But I'm going to talk. What I'm going to talk today, I'm going to talk about the whole journey and kind of take you through my journey and how I figured out how to build green applications, and kind of what I figured out along the way. Kind of what are the really important things you need to know if you want to have a good impact when building green applications. So that's kind of what this is going to give you the big lecture, the big overview of that. Now, when I first kind of realized I wanted to look into this space, I asked around, I asked friends of mine. One of my friends was in the Green Party in the UK, and I reached out and I said, look, I need to know, where can I find out this information? And they suggest join the community climateaction.tech. And I joined that community. Now I'm a co-organizer of Climate Action Tech. We're, I believe, one of the largest tech communities in the world that focuses on climate. And inside there, you'll just find we're a few thousand people right now, and you're going to find experts in pretty much any area. We're going to be in Climate Action Tech. We're a Slack group, and you can ask any questions inside there. It's a very vibrant Slack group. You always get answers. So I really recommend you go join that. But I went and joined that, and inside there, I got some great advice, and I made some great friends. And through that, we started to they taught me a lot of things, to be honest with you. But a lot of the stuff I learned still is in kind of academic papers or in lots of different books out there. So what I realized we needed to do is we need to get the knowledge really condensed down into a core set of what I realized were principles. Because it's not about knowing how to do something. It's about, that's not where we are right now. We need to know how the world works. That's where we are. Like we need to figure out kind of what are the principles, what are the things you need to know so you can make good decisions. That's where we are. I can't just tell you to make these decisions because it depends 1000% on what it is that you're doing. But if you have the underlying knowledge, you can then make the hopefully the right decisions for yourself. And kind of this is a growing field. And if you make the right decisions, write about it, talk to me about it. Let's publicize it. But anyway, we created what's called the Principles of Sustainable Software Engineering. If you go to the website principles.green, you will find it. And these are 8 core principles that you need to know. Principles that you need to know. And if you know these principles, you will then be able to build green applications or have an effective impact upon the carbon emissions of your applications. Now, I didn't come up with the name sustainable software engineering. I believe it came up in various meetings by the Mozilla Foundation, but I would argue that I'm the first person to kind of get it all down into kind of an easy to understand kind of website and kind of really get some structure around it. And I argue sustainable software engineering is an emerging discipline at the intersection of climate science, software, hardware, electricity markets, and kind of data center design. It's a much broader level of knowledge than you maybe are used to when you're working with other systems, like just narrow fields of software. You have to understand much broader depth. So let's go through. I'm going to go through them hopefully in quite fast speed. I'm going to go through all eight of them. Hopefully, let's see where we get to. So the first one is carbon. So my first problem was I realized that when I said green, it means different things to different people. Okay, what does it mean to you? What does it mean to me? It means different things to different people. So let's get on the same page. Let's all be aligned regarding what does green mean. Okay, what does sustainable mean? What does the word sustainable in software engineering? What does that mean? What's our goal? And the goal is carbon. So what do I mean by carbon? Well, I'm talking about greenhouse gases. So greenhouse gases are acting as a blanket warming up the planet. They're a natural phenomenon. That's a really important thing to understand, because that's a common attack that comes back to you. It's a natural phenomenon, 100% natural. The greenhouse gases in the atmosphere increase and decrease slowly over thousands and thousands and thousands of years. And that results in temperature increasing and decreasing over thousands and thousands of years. What's happening now is because of human activity, the amount of greenhouse gases has shot up in the atmosphere, and it shot up too fast to adapt to. Okay, we can adapt to anything, but when things happen too fast, we don't have time to adapt, and that's when lots of terrible things happen. Animals can't adapt, so they can become extinct, and even humanity. I mean, we can't really move cities like that, right? Okay, and there's billions of people living on this planet. So how can we, our ability to adapt, we don't think we can. And that's the problem. Not the fact that it's happening, but it's happening too fast. That's much more complex than that, but that's the core story, okay? So there's many different types of greenhouse gases in the atmosphere. All of them have a warming effect on the Earth. The most common is carbon dioxide, but there's many, many others. For instance, methane is another common one, and it has a much greater warming potential than carbon, between like 20 to 80 times, because it decreases over time, the warming effects of carbon. But it gets really, really complicated when you talk about greenhouse gases, if you had to talk about each and every single one. So we normalize everything into what's called carbon dioxide equivalent. So when we talk about 1 ton of methane, I'll actually describe 1 ton of methane as let's say 80 tons of carbon, or 80 tons of carbon equivalent. So we normalize everything into carbon. It's not the only greenhouse gas, but we normalize everything into carbon. And we also then just shorten it into carbon. So that's why we call it just carbon. When we say carbon, we mean all of the greenhouse gases. And so when I talk about this stuff, I'm talking about being carbon efficient, which is really the opposite. To explain efficiency, let's talk about waste. And I come from this position. This is my position. There's many different positions. And again, sustainable software engineering takes a position. I come from a position where we're always going to be emitting carbon. We're always going to be emitting carbon. I breathe, I emit carbon. Okay, so the goal, the direction we have to face and the things we need to do is to become more efficient. Okay, our goal might be different. Our goal might be to have 0 emissions or something along those lines. But the direction, the thing we need to do to get there, is to always focus in on carbon efficiency. It's no good just saying that's our goal, go do it, if we don't give people the direction they need to go in. So our direction that we always face as sustainable software engineers, when we're looking at a solution and we're trying to figure out which is the solution we should choose, we choose a solution that is more carbon efficient. Which really means for every gram of carbon we emit, we're getting the most value out of it as possible. And I think when I talk about green, it's about efficiency all the time. Okay, when I talk about sustainability, it's about efficiency. Okay, that's where I think about it. I think a great example of this is petrol-powered cars and electric vehicles. And I think let's just go through this example. When we take the black is petrol-powered cars, let's look at how wasteful it is. When we get the oil from the ground and we turn that crude oil into petrol, we lose about 50% of the energy potential in that oil is just gone. It just disappears. Diesel is less so. Diesel we only lose about 40%, but petrol we lose 50%. Petrol weighs stuff, so we need to get that to a car, and then we lose kind of another 20% because it weighs. We have to ship it around the world. It weighs stuff, so we lose that. But then an engine in a car, an internal combustion engine in a car, is only about 20% efficient at turning the petrol into forward motion. Okay, so then we've got 8%. I don't think anybody should be proud of 8% efficiency. But anyway, that's the efficiency we have with internal combustion engines. I would argue, if this thing was 10 times more efficient, we wouldn't be having the same problems we're having today. Okay, there's many arguments you can make that we still will, but if you think about it, if we're 10 times more efficient, would we be in the position we are in today? Maybe we'd just burn more petrol. I know that, but like, would we? So then let's look at electric vehicles. So when we talk, let's say we got the energy from solar panels. We consider that 100% efficient because that sunlight was going to hit the earth anyway, and it's also free, right? So we take it, and once you paid for the solar panel, it's 100% free. So you get 100% of that solar energy we get. Taking that electricity to a car is very efficient. That's very conservative, 2% loss. Very conservative. It's getting that electricity to a car. And I might have the wrong number here. I apologize. A typical electric vehicle is about 60% efficient, 60 to 70% efficient at turning electricity into forward motion. So I think 75% is incorrect. Oh, so it's probably more like 70%. Okay, 8% and 70%. That's what we're talking about when we're talking about being green. We just talk about being efficient. We just want not wasting, right? That's our world. And so we're just talking about being carbon efficient. Okay, we're emitting some carbon to implement this functionality. Let's make the most value out of it as possible. If you show me a developer that doesn't care about efficiency, I'll show you a developer I will almost certainly never want to hire. I never want to work with. Okay, it's efficiency. We all care about efficiency. We always care about efficiency. But what are we optimizing for? Let's optimize for carbon. So that's kind of why the first principle of sustainable software engineering is to build applications that are carbon efficient. This is the most important one. If you're faced with a decision, you're going to pick the one that is the more carbon efficient because that gets us to our goal. The second principle is electricity. So when I think of electricity, I think of electricity as clean, or I used to think of electricity as clean. When I plug something into the wall socket, I think of it as green. My hands don't get dirty. There's no smell. It's clean, right? But the reality is, electricity is one of the most dirtiest things on the planet. That's because most electricity is still created through the burning of fossil fuels. Not in France. France is very, very good. Most electricity is still created, I believe, through nuclear power, but it's still low carbon. But generally throughout the world, about 80% of electricity is created through the burning of fossil fuels, namely coal. And it's responsible for about half, a little bit less than half of all the carbon pollution in the world. Well, it depends country by country, but it's kind of around there. So now your brains are probably working. You're probably thinking, well, actually, how can my software consumes electricity? I'll just rewrite everything in C or Rust or something along those lines. Before you go that direction, there's many other lower hanging fruit that you can take into account. But yes, that's generally the kind of right direction to at least be thinking in. But now we need to get clear. Now we need to understand electricity. I believe electricity should be literacy. I believe electricity should be taught as module 1 in any computer science course or degree or something like that. How could I have reached this advanced stage in my career without really understanding the thing that fuels all of my computing? It's incredible. I think it's shocking that I didn't know how electricity works. Nothing I do works without electricity. How can I not know how it works? Anyway, I now really am researching a lot about electricity. It's actually quite a very fascinating space, I think. But let's talk about what you need to know in order to understand about electricity. The first one, what is a metric? The metric we're going to talk about a lot in this thing is kilowatt hour. And this is a measure of a volume of energy. A volume of energy is kilowatt hour. A kilowatt is a flow of energy. So a kilowatt is, and in fact, a watt is a flow of energy. A watt is a joule. A joule is the scientific unit, and it means a volume of energy. A watt means 1 joule per second. It's a flow. A kilowatt means 1,000 joules per second. And a kilowatt hour means, what if you left that on for an hour? What is the volume of electricity you would get at the end of all of that? That's kilowatt hour, and that's a common term that you will use or you'll hear when talking about it. So it's very important to distinguish between whether you're hearing kilowatt, which is a rate, and kilowatt hour, which is a volume. Before we go too much deeper, let's talk for a second, because I've just made you really upset about electricity. Okay, electricity is this huge part of the problem of the emissions in our world right now. Okay, and you might think, oh God, electricity is so awful, but also electricity is a huge part of the solution. Everybody's so excited about electricity as the solution. And that's because let's have a look at how much energy. This is energy I'm talking about. I'm going to give you some numbers now, and they're going to be general energy numbers, not just electricity. But let's look at how much energy the world consumes. How much power, I should say, the world consumes. So it's 18 terawatts. Remember, terawatt is a rate per second. Okay, so 18 terawatts is the world consumption. So all the damage that we're doing to the world right now, all the harm that we're causing, all the emissions that we're pumping out, they're to get 18 terawatts of energy. That includes kind of burning petrol and electricity, everything. Let's have a look at, but there's 1,000 terawatts available from wind. Okay, and a lot of that's offshore wind, things you don't see with your eyes. Kind of offshore wind is where everybody's getting very, very excited about, because no one wants a wind farm next to their house, but who cares if there's a wind farm far away in sea somewhere, okay? And admittedly, to get that 1,000 terawatts, you have to trap every single gust of wind on the planet, but there's 1,000 terawatts available. A lot more than we consume. A lot more than we consume is available through wind. But the crazy thing is how much is available through solar. 173,000 terawatts is available through solar. Now, admittedly, you'd have to have a solar panel the size of the Earth to get 1,700. But at the end of the day, we have 10,000 times more energy available to us via solar than the world is consuming right now. Electricity is a big part of the problem. Electricity is a huge part of the solution. Okay, it's a huge part of the solution. Okay, so don't get all upset about electricity. Electricity is fantastic. We need to electrify everything. And if we do that, it's not everything. It really isn't everything, but it's one of the quickest things that we can do right now to have an impact in the next 10, 20 years. But really, that's why the second principle of sustainable software engineering is to build applications that are energy efficient. Okay, they're energy efficient. Typically, we don't typically look at that unless you're building a mobile application. We don't typically look at that, but that's our goal, is to build applications that are energy efficient, because electricity, you can draw a line from electricity to carbon. And since our goal is to become carbon efficient, our goal is to become electricity efficient. That's the way you need to think about things as well. Can you draw a line from this resource that you are consuming to carbon? If you can, then that resource is a proxy for carbon, and you need to be very efficient with it. I listen to this podcast. I really recommend you listen to this podcast called The Energy Transition Show. It's one of the few podcasts I listen in the sustainability climate space that really gives me a lot of hope. And it's not really about sustainability; it's about energy, and it's really about talking about that there is a transition happening. There's a transition happening from fossil fuel powered to renewable or low carbon powered energy. It's happening. The only question is it going to happen slow or fast? There's going to be a huge amount of money that's about to be made. Depending on which side of that fence you land at. There's some company, and I think that's kind of what this podcast really gets me excited about. Okay, that there is a solution here if we accelerate this transition. There's something that can help us get to meeting kind of our targets if we accelerate this transition. And it taught me many things. One thing it taught me was about carbon intensity, and that's this idea that not all electricity is born the same way. Okay, some electricity is created through the burning of fossil fuels, and some electricity, as we just described, is created through the burning through renewable sources or low carbon means. And there's this measure of carbon intensity which tells you how dirty or clean is your electricity, and it's grams of carbon dioxide per kilowatt hour. Now we understand why I was explaining all these terms before. Okay, we have to understand this. Grams of carbon dioxide per kilowatt hour. The global average in 2019 was 519 grams of carbon per kilowatt hour. France is regularly under 100 grams of carbon per kilowatt hour. Plenty of other places in the world are above kind of 1,000 grams a kilo per kilowatt hour. But that's how dirty and clean your electricity is. And there's a great company called it's called Tomorrow, but they have a product called Electricity Map. And I just took a video of myself using it. So if you go to Electricity Map, you can hover over different electricity grids in the world, and you can see it's telling you what is the carbon intensity? Why is it not given France? That's interesting. What is the carbon intensity of the electricity? And you can see in some countries are much, much worse than others. And that's because some countries just have more renewables than others. Some countries, like Australia, famously burns a lot of coal. India famously burns a lot of coal. America famously burns a lot of coal. And other countries kind of famously use a lot of renewables. So because they just have more wind farms and more solar power plants in those regions. So by different regions, the electricity is different for different regions. But also the carbon, so I should say the carbon intensity is different for different regions because different regions have different kind of energy sources. But it also changes over time because let's imagine this scenario here. Um, we're in a region, okay, and everybody's using a certain amount of electricity. There's no storage in the system, not really. There's a few batteries, but tiny percentage. What happens is if you turn on your TV, the utility plant has to kind of create electricity to match exactly what you're consuming. That's how all the utilities in the world work. So if there's a lot of solar and wind right now, a lot of electricity is coming from solar and wind, and then the utilities go, well, we'll only burn a little bit of coal and gas to kind of meet the rest of the electricity. So therefore, the carbon intensity is quite low. But then the wind and solar kind of goes down. The variable sources of electricity. So what then happens is that utilities go, oh God, we need to get more electricity. Well, let's burn more coal and burn more gas right now. And then the carbon intensity increases. So over time, the carbon intensity increases and decreases. Okay. So now you're probably thinking that, well, I can probably build applications, or maybe I'll choose a region. If I have a choice of the region, maybe I'll pick the region with the averagely the best carbon intensity. Or if you want to be more real time about it, you can get feeds that give you real time data about the carbon intensity. So one of them is carbon-intensity.org.uk. If you're in the UK, this is a completely free resource, completely free. You don't even need to have a username or a login or anything like that. It's a free API. You can hear and it gives you the real time carbon intensity of the UK grid. What Time is a US non-profit, and they tend to have better data for the US stuff. An electricity map I showed you just before. This is more European companies, tomorrow's European startup, French slash. I believe they're based in France. Actually, now that I think about it, I believe they're a French startup called Tomorrow. Might be Danish. I'm not 100%. And they have their product called Electricity Map as well. And they have better data, I would argue, for Europe. They have, all of them have data for, well, What Time Electricity Map have data for the whole world as well. So these are sources you can go to get that carbon intensity data in real time, and then you can make decisions about where you run stuff, which has the list, so it has uses the less carbon intensity. That's the third principle: consume electricity with the lowest carbon intensity. I think I'm going to run out of time, so I'm going to jump through the next two as fast as possible. So I remember this is actually me speaking at a conference. I think it was in Poland. Yeah, this is me in Poland. And you can see from the slide at the front, I was definitely giving a talk on climate change. Not this talk, a slightly different talk. And just to bring everybody up to speed, we used to speak in person. We used to go to these things called conferences and used to go in person. And I used to stand on a stage and give this presentation and ask your parents. But anyway, what would happen after one of these? After I give a presentation, every time I give a presentation, we finish the talk and I stand to the side. And there's usually I get a number of people coming up to me asking me questions. Maybe I get questions virtually with this one. And I remember this was so funny because this guy kind of had been waiting in the back of the queue. Had a lot of questions. A guy waiting in the back of the queue eventually got to the front of the queue to speak to me, and just said, it was a great presentation style. Great presentation style. Love your presentation style. But you used a laptop, so I can't believe anything you said. And it really got confused me because I thought it was really strange. I didn't understand what he was talking about. What it boils down to is that because I used a laptop, and a laptop, when it was created, kind of released emissions, how dare I talk about the climate? Which is kind of one of these whataboutism. It's a really dumb argument. And I get it all the time. But what I think it's hilarious that this guy like sat in the audience throughout the entire talk, didn't walk out, but sat in the audience, angry at what I was doing, came down and queued up for a long time to come speak to me to say he didn't believe a word I said and then walked off. I thought it's funny. I thought it was a great example of this. So, and what he's describing is this concept called embodied carbon, which is absolutely 100% true. Everything releases carbon. When he created this, headphones release carbon to create it. You know, all kind and people measure this. We measure this. We know what this is. Okay, there's an entire field of study which just sits down and measures the carbon cost of everything, including MacBooks, okay, or laptops or Surface. We have our own team in Surface which does it as well. And it's absolutely true. It's absolutely true that there's and it's oftentimes quite high as well, and it depends on what it is. An electric vehicle has an embodied carbon cost that is about equivalent to about 4 years of usage. So after 5 years, I think, of usage, so after 5 years, it's paid off that carbon cost, and then it's kind of like carbon free. That's the way to think about it. So, and the same thing happens with servers. The same thing happens with servers. They have a carbon cost, and it's quite high. It's often quite high. This is just an example. Let's take an example that a server had released 4 tons of carbon in its creation. How do you think about that? Well, you amortize that over a number of years. You say that, well, server usually maybe the lifetime is about 4 years, and you spread it. Then you say that, well, actually it's about 1 ton a year, and then you can kind of like think about it as a continuous amount that you're releasing rather than a sunk cost that you've already spent. That's not a good way to think about embodied carbon. Spread it out across the lifetime of the product. As a great example is if you look at a specific server like the R640 Dell server, they released numbers. The embodied carbon is 1.2 tons. And if you assume a 4-year lifespan, that's 320 kilograms a year. If you choose a European energy mix, I chose a European energy mix, which is quite clean. It's 486 kilograms a year if it's kind of maxed out, a max utilization. And so the yearly total is 806, and therefore about 40% of the yearly total is from the embodied carbon. Okay, so it's quite a lot, right? We talked about electricity for ages, how making it energy efficient. There's almost nothing you can do, is there? If you made your application the most energy efficient you could possibly make it, it's still emitting carbon because the server emitted carbon. So then I kind of like thought, well, what does that mean? What does that mean from a software engineering perspective? Because embodied carbon is kind of this important thing to know, but so what? Like, what as software engineers, what can we do about that? It's like it's hardware. It's already been spent. And I think the way to think about it is, I think a good way to think about it is like a lifetime. Like we assumed the hardware would last 4 years, but actually, what if it lasts 5 years? Okay, why are we actually even getting rid of that server? Okay, sometimes, I mean, servers rarely like break down these days. There's no moving parts. Like you're just making a decision to end of life something and bring something else back in. From a cloud perspective, we're making very complex decisions like, well, this space in the data center costs money. At what point do we make less money from the hardware, and kind of what point do we take it out? And it's not, Microsoft don't throw it away. We're now building these circularity centers. We kind of break them apart. We use them as spare parts, or we resell them onto others. We don't throw. We're going to move to a model where we're not throwing anything away. But essentially, that's how to think about it from a software perspective. How do you make hardware last longer? How do you make it so that I don't have to buy a new mobile phone every 3 years because none of my old applications work on it? And so if you think about it in that way, okay, if you then just say assume a 5-year lifespan, you've dropped the yearly total of the embodied carbon by 9%. Okay, so that's how you can have an impact on the embodied carbon. And really, the way I describe this as is hardware, right? We just pointed out hardware has embodied carbon. So hardware is a proxy for carbon. So if we need to be carbon efficient, we need to be hardware efficient. Okay, we need to efficiently use our hardware. Okay, that's the way to think about it. Efficiently use your hardware. And there's many things this could point to. Many things this could point to. But one of them is just don't throw away hardware that is perfectly valid and needs to be used. Reuse it, recycle it. As many from a software perspective, make it last longer and make your applications run on older hardware. There's many arguments you can put to this. I'm gonna maybe just do the next one and then go from there. So this is like a really interesting one called energy proportionality. Now, to understand this, I had to really dig into the hardware aspect of servers. And it's essentially about this really interesting concept in hardware, which is the more you use hardware, the better it becomes at turning electricity into useful operations. The more energy efficient it becomes. Okay, the more you use hardware, the more energy efficient it becomes. It's a really interesting aspect of hardware. Kind of what it boils down to is something along the lines of this. So utilization is kind of how you utilize a server is, or even a computer. And at 0% utilization, you're still, this is just an example, you're still consuming power. Let's say this is an example, 100 watts. So even when your server is 100% idle, it's still consuming power. That's because there are so many things, parts of a server, which consume power regardless of your utilization. Your network card, doesn't matter if you're not utilized or it's still consuming the same power. Memory, still consuming the same power, whether you're using it, whether it's full, whether you're not using it. Spinning disk hard drives, yeah. But also CPUs and GPUs, like per core, there's a static amount of electricity that's always going to be used, whether it's 100% utilization or 0% utilization. So the more cores a CPU has, the more utilized it, the less, the more static power draw there is. And what it also means is so basically what this means is that when you're not using a server very much, it's still consuming electricity, and its energy efficiency is really, really bad. And the more you use a server, the more energy efficient it becomes. Okay, and what that kind of leads to is this argument that kind of two servers at half utilization would be consuming 360, maybe 360 watts of electricity, whereas the same work, if it was performed on one server, might be only consuming 200 watts of electricity. So this is kind of this idea of energy proportionality. So, and I didn't understand anything about energy proportionality at all as a software engineer. Hardware people who design silicon, they very well understand this. People who design data centers and ops people who kind of really focus on data centers, they really understand this concept as well. And your average on-premise, so not hypercloud like Microsoft, but your average private cloud, it's estimated that there's some good reports from I forgot the name of the organization, but there's some good reports, studies that show it's between 10 to 15% utilization. That's it. 10 to 15% utilization on average. Not Microsoft's clouds, not hyperscale clouds, but your average private data centers. So as well as you're breaking the previous principle on embodied carbon because you're using hardware efficiently, right? You're also breaking the energy. You're also using because of energy proportionality, the energy efficiency of your hardware is so much less because you're utilizing it very, very low. And that kind of leads to the next principle, which is maximize the energy efficiency of hardware. Maximize the energy efficiency of hardware, and that requires kind of understanding a lot about the hardware, because it does actually change, but generally it means utilizing it more, means you're being more energy efficient. But there actually are many more cleverer things you can do. That you can change the clock frequency, you can do a number of different things, but to do these things you have to understand hardware. And I spend a lot of my time now talking to people who design silicon on a day-to-day basis, because that's where the efficiencies will come along. I'm going to zoom through the rest of the networking is another one. Networking is just servers, it's just computers, right? And so it consumes electricity. It has embodied carbon. There's many different carbon costs from networking. But but we think the two big ones are the amount of data and distance it has to travel. Okay, so we know that we're very certain that if you send more data, it emits more carbon, and we're very certain if you send the same data over a longer distance, it emits more carbon. So with networking, reduce the amount of data and the distance it has to travel. From a web perspective, this would mean using edge nodes like CDNs. From a application development perspective, maybe it means building less chatty applications, doing a lot more processing on the database side and sending skinnier data down. There's many things this could mean, but essentially reduce the amount of networking. Demand shaping is really interesting, but I could do a whole session just on demand shaping, but essentially it's this idea, which is when you have a resource that's constrained, instead of trying to get more of the resource, demand less. Okay, demand less. So a great example of this is video conferencing software, I think. So with video conferencing software, when the bandwidth is reduced, the software just doesn't go, whatever, I still want to get my same frequency. I still want my same resolution. I don't care. I'll give you my same resolution. No, the software goes, oh, okay. Oh, you don't have enough bandwidth for me. Okay, I will reduce my demand. I will reduce my resolution. I will switch off video. I will prioritize audio. Lots of things do this, okay, but we need to start doing this from a carbon perspective. So when the carbon cost of something is high, which we either know by measuring it directly or by looking at the proxy to something to carbon, then reduce our demand. I think a great example of this is perhaps one of the things we do know from a website is, or from networking again, is that if you are connecting in through a mobile network, so 3G, 4G, 5G, something like that, it's many multiples of times more carbon inefficient than a Wi-Fi or a wired connection. Many more times. So from a website or an application, if you know that your user is then connected through a mobile network, change the demand. Change the features of your application. I call it making a carbon-aware application. So you're changing the user behavior. Maybe you give the user an option. Do you want to go into eco mode? Do you want to make a voice? Do you want to make a video call? Do you want to make a voice call? Because the carbon is quite expensive right now. That's demand shaping. And what demand shaping is here also just to bring in user experience designers. This whole thing, sustainable software engineering isn't just for software development, just for software engineers, just for people who write code. It's for everybody involved in the creation of software. So if you're a user experience designer, if you're a designer, can you design applications that demand shape, that are carbon aware? I think a really great example of this is I hope I've got her name, like Yulin or Yuli. She made she's a designer, and she made a proposal for a carbon aware operating system called Online, ONLIGN. You can Google it. And she proposed many different features that an operating system could have, where if the carbon was high, it would then pick lower carbon options and therefore demand shape. I'm going to zoom ahead. And the second is optimization and measurement. Now, I'd say here is the really important thing about optimization, and I hope, is again, we're building carbon aware applications. It's very hard to measure carbon. So if you can proxy something back to carbon that is easy to measure, then use that as a measurement criteria. You can measure carbon. It's quite difficult. If you can, use that and just reduce as much as possible. As I said, electricity is a proxy for carbon. It's oftentimes easier to measure. There's various tools out there. They're not that easy, but they're there that you can measure electricity consumptions of your applications. If you reduce electricity, you reduce carbon. So to use that. Cost, at some level, the cost, carbon is factored into the cost of applications. Okay, and so reducing the cost of your application almost always reduces the carbon. So yes, carbon efficient green applications almost always cost less. Networking. So again, mentioned before, like that's a proxy for carbon. So reduce the amount of data and distance has to travel, and then we know that reduces the carbon. Performance. You can always increase performance by throwing 50 more servers at the problem. But if you have the same compute, and for the same compute, you make your code more performant, then that, we know that's a proxy for carbon, and that reduces the carbon as well. And again, a lot of this stuff you'll be thinking, actually, that makes my applications cheaper, faster, probably more resilient. Yes. A green application is almost all of those things. And that's why, yeah, optimization. So there's a summary, and you go to principles.green. You can find them all there. You can apply. We're now working on trying to get a lot more concrete information. Some of that's going to appear in principles.green. In fact, a lot of that's going to appear now on our website, docs.microsoft.com, and Microsoft documentation. We're working through how to figure out how to do all the Microsoft products more, all the services, how to do them more sustainably. And we've also launched a blog called Sustainable Software Engineering, and it's on Microsoft, and we're writing every single week. People from all over Microsoft who've been working in this space. This is a platform where we can basically talk about our stuff. So if you want to catch up and stay up to date with kind of the latest stuff that we're working on, or people are thinking about, or head to the SSE blog and you'll go there. Before I leave, I just want to say there's also two philosophies, and it's very, very important. There's two philosophies of sustainable software engineering as well. And the first one is that everybody has a part to play. Okay, everyone has a part to play. With sustainable software engineering, what we're figuring out, or we want to figure out, is what is the solution for everybody, whether you're a front-end engineer, a back-end engineer, a user experience designer, whatever your part to play, whoever you are, there's something for you to do. Everyone has a part to play, okay? This isn't just, we're only going to focus in on database people because they cost the most carbon. No, everyone has a part to play in the solution. And the second philosophy is that carbon is enough to justify what we do. In the past, we always had to wrap sustainability in these little pills to make it easier for people to swallow. We were too embarrassed. We knew if we said we were doing something because we were being green, no one would care. That's changed. That's completely changed. The existence of this conference means that has changed. Okay. Now, if you're a sustainable software engineer, you are building your applications, you are doing it for the sake of sustainability and nothing else. That's why you're doing it. Yes, they're cheaper. Yes, they're more performant. Yes, they're more resilient. But those are added advantages. They're not the primary reason you're doing it. The primary reason we are doing this is for sustainability. The rest of these wonderful benefits we can use as arguments to help push our cause, but we're not saying we're doing it to make applications cheaper. That's not our primary goal. Our primary goal is sustainability. Those are two philosophies. Thank you very much for your time.
So, thank you everyone for watching this talk by Asim on sustainable software engineering. And now I'm going to call Olivier to announce the next speaker. And just before that, just a word about Asim. Asim is actually right now on YouTube. We've seen him in the comments. So feel free to write him a little message, ask your questions, or you can also ask him anything on Twitter at Jawash. Thank you. Olivier, if you're ready, we're going to announce our next speaker.
Hello again. So I'd like to ask David to join me. David, I think David is around. Hey, hello David. How are you doing?
Doing good. What about you?
Well, doing great. A bit cold here, but doing absolutely great. We have a lot of people in the conference, so no pressure. So David, you're going to talk about, so you're a web developer, so obviously you're going to talk about quantum computing, right? That's what I understood.
Well, quantum computing is a personal passion for many reasons, and I think it could be linked to this conference. There is some high hope that quantum computing could help sustainable, engineering, building some, new hardware and trying to solve some issues around on the planet. But I'm a web developer. I'm leading pwbuilder.com, which is an open source project to help people building PWAs. And I want it to be more concrete, I would say, that quantum computing.
You're going to save the planet anyway, right?
Well, we all try.
It's a work in progress. Okay, so David, you're going to talk about building green privacy web apps, and I'll leave that to you now.
Yes, I'm going to share my screen. And you should see it. So hello. So my name is David. Yes, working at Microsoft Corp, and I wanted to check if it was possible to do something as a web developer to try to reduce the carbon footprint. So I decided to name this session "Building Green Web Apps," even if Asim just explained before that grid doesn't mean the same thing for everybody, but you got the idea. Is how to optimize maybe what we are doing as web developer and reduce the carbon footprint of what we are doing. So I'm going to share the story, how I've been working on that. I have really no clue at the beginning. I'm working with a colleague at Microsoft France named Pierre Lagarde, and we wanted to check if it was possible to reduce the footprint of PWA. And I started doing some researches, and this is the outcome of those researches. So the agenda would be, why should we matter, building a PWA that could be more green or more efficient? Then we will see on which kind of devices the PWA are running. So are they going to run, on smartphone, desktop, and what the impact we can have there. We will see a bunch of tooling I've been able to find to measure the energy consumption of a web app. And at last, I've done a couple of benchmarks using those tools to check if it was, relevant to try to optimize the PWA, what could be the impact on energy consumption. And I will finish for idea I've got for the future because, well, I haven't managed to check everything I wanted. So I'm going to share those ideas, and maybe some of you will be able to share your thoughts there. So why should we bother about PWAs? Well, I think that you all know that web apps are everywhere. All the time we are using web apps, we tend to even to forget about that. But there is three main sources of energy for web apps and for PWAs. Obviously, we talk about hosting just before. So where are you going to host your the server that's going to serve your PWA could have already an impact. Then you will have the quantity of data you're going to transfer on the network infrastructure. So you can act on hosting because it's up to you to choose the best hoster that is the most efficient. For network infrastructure, it's more difficult to be able to impact that as a web developer. So we cannot really try to act there. And for the client, this would be the main center of interest today is, can we really modify our client code of our PWAs to be able to be more efficient? So I think Asim already shared this site, which is really interesting. France is well known to be low carbon because we have a lot of nuclear, electricity being produced by nuclear plants compared to our neighbors that are using more, coal or less efficient energy. So first, if you're living in Europe, like in one of those countries, it may be a good idea to think about using France in a way to store your data. So if you're using Microsoft Azure, for instance, we've got data centers in France. If you're using AWS, same, they've got data center in France. So then you need to think also about, if you put that in France and you're living like in Russia, we need to evaluate if it makes sense, because then you will more use the network infrastructure and you will lower down the latency. So, but it's interesting to see that at the beginning, just for hosting, you can already make some choices that can impact the carbon footprint of your PWA. But I would like, as I'm not a huge expert in this area, and many other speakers will talk about, the cloud part, I will focus more on the client part. And for that, I like to talk about why should we work on PWA. So they are highly used on desktop web app. So we recently shared that on the percentage of usage of an app on a desktop could go up to 60% in a web browser. So meaning that the user, the Lambda user, is going to spend most of his time in the browser. So if you are a web developer, this is where you can act to reduce the footprint. And it's more and more popular on smartphone, even if on smartphone, a lot of people are using native apps rather than web app. But we know that PWA, Progressive Web App, can really be close to the native experience, and more PWA are coming on Android, at least, and a bit less on iOS. So service worker, if you don't know what a service worker, when you're building a progressive web app, is a small piece of JavaScript that live between the clients and the backend. So it's being run on the client, but it's like a proxy that's going to catch every request. And then you will be able to have a smart cache that can improve the performance, enable offline, but also going to reduce the network bandwidth. And then it's going to help to build more efficient web app to save some energy. So first, let's review the various devices where you can run PWAs. So it was stupid jokes like you can use the same with Chrome, inspect devices. So it's something that you usually use when you connect your smartphone to your PC to debug it. So and I wanted to really understand what was the main source of energy on both worlds like desktop and smartphones. So I was thinking like that. In my mind, there was the usual suspects. So the usual suspects are, well, the CPU, GPU, network, sensors, and screen. So I don't know if you know this awesome movie, but I've put this the most impactful on the bad guy, and I wanted to really understand where is the energy lost, and can I act on the specific, hardware part as a web developer. So let's start by the desktop. So obviously it's going to depend on the type of CPU you're using. So if you're using a low-end CPU or high-end CPU, it's going to vary a lot. So, but it goes from 55 watts up to 150 watts. So the CPU is going to consume a lot of energy on desktop. So we could already guess that. But this is where we need to then improve our code. And for the motherboard, which contain, the network interface, going to contain the Bluetooth, Wi-Fi most of the time, sometimes the video card also. So we see that it's going to consume less than a CPU. So if it's a regular motherboard, it could go up to 40 watts. And if you are a hardcore gamer, your motherboard will consume more energy. So this is the second one. So, but this is where we're going maybe to try to act at the network level. This one was interesting to my point of view. I was thinking like, if I'm consuming more memory, am I going to consume more energy? So I'm not sure about all assumption I'm doing. So as I was trying to measure energy in the second part of the presentation, but it looks like that if you have like a single memory of 8 gigabytes, and then you double that, it's not going to consume more energy. So it doesn't mean, for instance, I've got 64 gigabytes on this machine. So with 2 slots being used, it is not supposed to consume more energy if I would have 16 gigabytes. So it means that maybe this is not where we should optimize for the green part. We know that we should pay attention to memory for sure. And using more memory will less use disk. So it could be an interesting trade-off. But compared to CPU, you see that memory is not going to consume a lot of energy, and even more compared to the GPU. So GPU are more and more, available on obviously in dedicated way on PC, but also on smartphones. And as we slowing down the CPU, increase in power because of the Moore law that's slowing down, we are using more and more the GPU to use some specific task. And this GPU could consume a lot of energy. So for instance, the latest NVIDIA RTX cards could consume up to 350 watts if not overclocked, of course. But most of the time for low-end graphics card, it will vary from you see 25 up to 86. So you need to pay attention on are you going to use the GPU? For the hard drive, it's interesting. I think we all knew that SSD is consuming less energy than a regular magnetic hard drive. And you can see that except for 3.5 inches hard drive, it's not really relevant maybe to spend time trying to optimize the usage of it to save some energy, compare again to CPU and GPU. But still, it's interesting to see that everybody using SSD now is going to have better battery life than a regular hard drive. And at last, one of the most consuming source of energy. So this is my beautiful screen I've got in front of myself today, which is a white screen. This is not green at all. So it's consuming a lot of energy. It can consume more than 100 watts. It's not the highest consuming screen I found. I've got a list there. I was trying to evaluate the number of energy being used by various monitors. So it can switch from 20 watts approximately to more than 100. So it's high source of energy. Unfortunately, as a web developer, we have almost no control on that. And we'll see it's the same on smartphones. So it's more the user himself that need to pay attention to what he's paying. Let's switch to smartphone now. So to check if we can do a parallel. So smartphones are different, obviously, because the screens are going to be smaller, and then you have a mobility experience. So in case of smartphones, we can see that when we are in airplane, so the network stack is being, shut down. You're not using any kind of cellular connection or Wi-Fi. The most important source of energy will come from the system on chip, so which is the CPU, GPU, and several, hardware being stored there. The RAM also can use a little bit of memory, but you see still really not that high like on PC. And others could be like the rest of the smartphone. When you start to enable like 2G, 3G, or Wi-Fi connections, you see that the energy is going to really increase a lot. So the first time I've seen these graphics, I was saying like, why I shouldn't maybe use Wi-Fi, but we shouldn't think like that because it's going to consume more energy in a very specific, smart amount of time. So maybe I will use more energy, but I will download so much faster the data I need that will be more efficient at using 3G on the longer term. So we will see that later on, but it's not because at the specific moments you're going to consume more energy that you are less efficient. And this is something that I understood while preparing this session. So I was thinking about also, the sensors, accelerometer, gyroscope, and stuff like you've got on the smartphone and you usually don't have on the PC or Mac. You don't have to pay attention to that because I was thinking, would it make sense to lower down, the speed at which I'm going to get the data of the accelerometers, but it's not going to change a lot of stuff on the energy consumption. So let's forget about sensors. And this is the usual suspect. The bad guy is on the left. So you see that CPU, GPU, and the cell, so the cellular, connection to connect to the 4G or 5G now networks, are the highest source of energy consumption after the backlight. So if you have a LCD screen, so the LCD screen itself, as you can see there, is not consuming that amount of energy. Well, it's consuming like a bit more than the CPU, but the backlight is really what's going to consume much more energy if you're using an LCD screen. If you're using OLED screens, not the same technology, so you don't have backlight, but you see, we cannot act on backlight as web developers. And while doing some researches, and I'm really sharing that with you, that the true story, I found these graphics. And the first time I've seen this graphic, I say, wow, it seems like blue light is consuming more energy than green light or red light. So I start to think about how I don't know how this is possible. So I try to really think about, the wave of the lights and maybe it's linked. So I've been able to find this Planck equation. So it's a way to measure the energy of photons. And as it's based on the wavelengths, it's going to explain why blue energy is consuming more energy than green or red. I said, wow, maybe it's something I can do as a web developer is try to optimize my web design to use less blue energy and maybe more red colors. So let's try to measure that. So is it useful? So sometimes you may ask some question yourself and you need to check if it's interesting or stupid. So I was in this state and I can give you the answer. The answer is no, this is not useful, except maybe to be fun during parties and try to impress people. But I really wanted to check that. So I've been building a simple web page that's going to put in full screen background color to blue, and on the other side, the background color to red. And I wanted to measure that. So I've been using this thing. So it's a watt meter. And I've been measuring that on an LCD laptop and on the Samsung devices using OLED. So the output is that. So using OLED, so OLED don't have backlights. It's the self-emitting technology. If I'm using a full screen using the blue color, you see I was consuming, so the smartphone wasn't doing anything. So it's using a very low quantity of energy. The watt meter was displaying 1.3 to 1.4 watts. Red screen was consuming a bit less of energy, 1.2 to 1.3, but you see the difference is not that high. And for black screen, it was using 0.9 to 1. So it means that if I'm shutting down completely, the screen, in the case of an OLED screen, you're going to lower down the consumption. In the case of the LCD doesn't work the same way. You need backlight. So when I was running my web page with pure blue, I was consuming between 13 to 14 watts, same for red and same for black screen. So it's only because the backlight is always enabled in a way, and this is really the element of hardware consuming the most of the energy. So don't bother to try to modify the color of your website. This is an idea I had, and I've been able to verify that this is useless. So I wanted to check a blog of a gaming influencer I like in France named julienchiez.com. And he's got like a black theme and a white theme, so light and dark theme on his website. So I wanted to check if it's going to impact the energy consumption, because this is something I had in mind too. So using the static page, so if you load the page and do nothing on it, the light theme seems to consume a bit more of energy than the dark theme on an OLED screen on my Samsung S8, but you see that this is very small. And when I start to scroll on the website, so you use the web page in a normal way, no difference at all. So I was a bit sad because I was hoping to be able to act on the screen itself, but the dark theme going to save a little bit of energy, so maybe we can do it, but this is not where we can have the most of the impact. Once again, same website being reviewed on my Surface laptop too, which got a LCD screen, and no difference at all between the light theme and the dark theme. So we need to find something else. So on the same, so I've been sharing the studies, at the bottom of the slides, and what they were saying at the end is that OLED display is dependent on the image content you're going to display, obviously. But you see that in my case, I was a bit sad because it wasn't a huge difference to my point of view. Also on LCD-based devices, the content has really small or a small impact on the energy consumption, a little bit, but I haven't been able to measure it during my tests. So if you're targeting OLED display, you can act a little bit on your web app, but don't expect tremendous differences. At last, on devices, something really important I found during the studies, and we will be able then to switch to the review of the various tools to measure that. You can see that if you're playing a low quality video on a smartphone compared to a high quality video, if you're using the GPU, so if you're using hardware decoding, it's not going to change a lot the energy consumption. You see this is 200 there, so meaning that the GPU will still be around 100. It's close to 100, and it was like a bit over 50 milliwatt being used between hardware decoding on high quality video and low quality video. But then have a look to the CPU if you're using the software decoding. So let's say that you're using a codec that is not hardware decoded by the smartphone, then you will have the CPU to do the job of decoding. And then the energy consumption is going to go super high because if you ask the CPU to manage more data, obviously it's going to increase in energy consumption. So this is very important to take into consideration when you have web app using media video content. You need to pay attention to the quality of it. Do you really need like 4K? And we will have some benchmark at the end. And pay attention to the codec you're using, because otherwise you will increase a lot the CPU consumption on the user device. So now let's see the available tooling I've been able to find from hardware to software. The first one is very simple to use. It's relatively cheap. It's like 25 euros maybe, or dollars, probably the same price. To be able to use it, you need to have like either your smartphone or laptop to be fully charged, because I've discovered that if you try to measure the energy while the adapter is charging your laptop or smartphone, obviously you're going to consume the maximum of energy of the adapters. So you need to wait for the battery being filled at 100%. Then you will be able to measure the differences of energy with the wattmeter. So if you're using that on the desktop, you don't have this issue, obviously, because we don't have battery on the desktop. But pay attention to that. Very easy to use, not super precise, because if you are running a task during less than a second, you won't be able to see any difference on the wattmeter. Obviously, the Windows Task Manager can also help you, because you will be able to see the CPU usage and the GPU usage. So you can even go a step down. Like in my case, I was trying to identify the specific tab I was trying to review, and you can see the amount of GPU usage. So, and we will see that this can have a high impact on energy consumption, as well as CPU. And then you have also some new columns in the latest version of Windows, that is the power usage and the trend. So you will be able to check in an easy way, but in a very high level way too, how your current web app is being optimized for power usage, just by going into the task manager. I don't know if you know that, but in Edge and Chrome too, if you're pressing Shift Escape, you can have also the browser task manager that going then to provide you some other detail, like the amount of memory being used. But we've seen that it shouldn't really impact the energy consumption, and then the GPU memory, and once again the CPU time. So the network too, I found that the network is not super precise, so it's not really easy to use the network column to be able to check the amount of data being sent and energy being used. But it's a way to first check how your web app is running. Of course, you have well-known tools like Lighthouse. Lighthouse is going to give you insight on the performance of your web app. But like shared before, performance also is correlated to energy also efficiency. So meaning that if your web app is super slow because you haven't optimized it, it's going to use a lot the CPU in a bad way, consume some energy where you could have optimized it to consume less energy. So Lighthouse is not designed for green reviewing, but it could be also a first step to help you. I wanted to use Android Studio too, because Android Studio can have an energy profiler, so to analyze APK. On pwbuilder.com, I can generate APK for PWA to be able to push the PWA to the Play Store. So I wanted to test it. Unfortunately, you cannot attach to a trusted web activity, which is a special type of APK to push PWA on the Play Store, because you should attach to a process you've been building. So if I'm building an Android app, I can inject a debug symbol and be able to attach on it and finally measure the energy consumption. And Android Studio doesn't seem to be able to attach to Chrome or Edge or whatever browser on an Android device. At least I haven't been able to find a way to do it. So if you know how to do that, I would be interested, because otherwise Android Studio seems to have a great way to do energy profiling. I've been finding this one really cool being done in France, I guess, by someone following me on Twitter. It's Green Spectre. So it's the same principle as PW Builder. You enter a URL and it's going to do a review of your website, like Lighthouse or many other sites doing the same approach. And then you will receive over email reports going to share the impact of your website on battery life. So I've been reviewing my own project, PW Builder. Seems that I'm not that bad. So it's a very interesting way to review your energy consumption. And I'm sharing the link there if you'd like to play with it. Another idea I had was maybe I can use the battery API available in the browser itself. Because Chrome, Edge, and other Chromium browser got it. Firefox used to have also an approach when they were building the Firefox OS. Unfortunately, I was a bit sad to discover that the precision of the level of battery is not good enough to be able to evaluate, the amount of energy I'm losing on doing a specific task. Because you see that is going to change from high value to another high value. So I cannot measure in a precise way what my code is doing. Otherwise, it would have been cool to put some timestamp, like let's do like something I know is going to take a lot of CPU, maybe, or GPU. Start the battery manager, record the state of the battery, and then at the end record the state of the battery, do differences, and be able to measure the energy being spent. But unfortunately, this is not useful in this case. But maybe there's other useful way to use the get battery. We will talk about that at the end. At last, this is a tool that I've been using for doing some benchmark. I don't know if you know that, but on a Windows machine, and same for other OSs, I guess, the OS can tell you where you're spending the most energy. So in my case, apparently, when I took this screenshot, it was in Microsoft Edge and Microsoft Outlook. So how do we do that? We're using a tool named Power CFG. And if you run this tool using this command line, and if you go on the blog Asim shared just before, there's also an article explaining you how to measure the energy consumption of an application, not specifically a web app, but of an application. And I've been using this approach to measure the energy spent by Microsoft Edge, in my case, to try to measure the number of joules being consumed by the various benchmark I've been doing. So let's jump into the benchmark and see if I've been able to save some energy. So let's start by trying to optimize at the CPU level. So we've seen on the hardware device inspection that the usual suspects are the screen itself, and I cannot really act on that because of the backlight, the CPU, the GPU, and the network, like the cell or Wi-Fi. So let's measure, I wanted to measure like WebAssembly versus JavaScript, because we know that WebAssembly can be much more quicker than JavaScript. So I've been modifying a sample that exists already, trying to do face tracking using an AI, deep learning type algorithm, and to track my face using the webcam. I cannot use it because I'm currently using the webcam to broadcast that, but I've been doing a screenshot. You can see that using pure JavaScript, I've been able to recognize my face at 2 frames per second, so it's super slow, and it was using approximately 10 watts when I was doing that. So when I was doing this, using this web page, 10 watts was being used to have 2 FPS. Switching to WebAssembly, I've managed to jump to 30 FPS, so much more faster. So it means that I'm using much better the hardware, but I'm consuming like almost 18 watts. So I was surprised. So I was thinking, so maybe is WebAssembly more efficient than JavaScript? Because sure, I have a much better experience, but then it means that I'm consuming more energy. So in this typical case, I think it's relevant to you try to reach the 30 frames per second with a bit more energy rather than 2 frames per second. But it wasn't a good conclusion at this stage. So I've been using another WebAssembly benchmark, a benchmark that's going to do various tasks to generate PDF, to search for text inside a PDF, various types of office type of tasks you could do on your machine. And this one was much more interesting. So first, when I was executing the same benchmark, doing the same task between JavaScript and WebAssembly was much faster, which is good news, like we've seen for the video benchmark. And the range, so this is where it's difficult when you use that, because I don't have on this specific device a way to ask for how many energy have you been using during this amount of time. So I have to look at it and try to evaluate. But what I've seen is I was consuming between 21 to 25 watts using JavaScript. There are some higher peaks on the WebAssembly, but generally the average usage was lower on WebAssembly. And then I tried to do something that is stupid, is trying to multiply the approximative average usage by the time being used, to say that even if I'm using more energy during a less amount of time, what's really important is the amount of energy consumed in total. So this is not any kind of units, it's a fake unit. That's why I've been using Power CFG. That's going to give me the number of joules being used during a specific task. And in this case, I've seen that I've been using less joules, so I've been able to better use the energy and be better for the planet by using WebAssembly for this specific task rather than JavaScript. So good news, WebAssembly could be a good friend to improve the carbon footprint of our PWAs. CPU, then I was thinking, we know that JavaScript is not good for CPU because it's mono-threaded by nature, but we have web workers, which is, well, something not as good as multi-threading, but at least we can start to better use the cores. And I wanted to check if it was the case regarding energy. So I've been using this ray tracing tool on my Surface Laptop 2. So my Surface Laptop 2 got 4 cores, which are hyper-thread, which means that I've got 8 logical cores. So what I've been doing is I've been executing the rendering of an image. So I've been modifying this specific demos to compute a 4000 by 4000 pixels image. It took 31 seconds to execute using one worker, so using like JavaScript by default if you want to. And it took 10 seconds only to be executed on 8 workers. Now the question is, was it better regarding energy? So obviously the approximate average of energy consumed on my wattmeters was 35 watts compared to 19 watts. You could say, wow, so it means that you're going to consume more energy. But the truth is that I've been able to better use the hardware. Like Asim was explaining before, what is really important too is to use the hardware in the most efficient way. And asking to Power CFG, it looks like that they've been using less energy in final, so 83 joules compared to 222 joules, because even if I've been using in a peak more energy, I've been using it during a less amount of time, so I was more efficient. So once again, web worker could help you to build the more efficient web app. So video quality. So we've seen that codec and the video quality could have an impact on your consumption of energy of your web app. So what I've been using with YouTube, so some video I've got myself on YouTube in 4K and some other 4K 60 frames per second videos. And this one is interesting. So as long as you're using a codec that is going to use a GPU, switching from the lowest quality up to 4K, I've seen 2 watts of difference of usage. So it could be interesting because saving 2 watts on every machine could have a huge impact. We can see that the GPU usage is going on. So I've been using the Windows Task Manager for that. So it was super simple. And it means that the more you will use the GPU, the more you will increase, obviously, the energy consumption. So you need to pay attention, because maybe my GPU was strong enough to handle that, but maybe on the lower GPU, I would use much more energy. On 60 frames per second, I wanted to check if the frame rate could have an impact. It doesn't seem to be the case up to full HD. Reaching 4K, I've seen that the GPU usage has more than double, which is relatively logical. And then the number of watts being used also increase a little bit. So it means, once again, don't provide 4K 60 frames per second to your user if they don't have like the screen to display it, or if you got a smartphone, it's meaningless to send a 4K video to that. And YouTube obviously is generating that for that, is managing that for that with the auto settings. And I wanted to share something. So we have a tool named E3 for energy estimation engine that is being run on the user machine to evaluate the energy being spent by some app. And this is an application we've got in the Microsoft Store using web technologies that is doing streaming. And we see that before the COVID crisis, well, the amount of energy was like that, and it started to increase during the quarantine, because a lot of people were stuck at home watching video content. And this is where some people and some streamers decided to lower down the quality of videos to avoid having network congestions. And we see that the energy being used by those applications on the machine decreased, meaning that it's directly correlated the quality of the video with the energy being spent on the device. So take that into consideration. Maybe you don't always need 4K or even full HD to watch some of the video content. Another interesting test, and we are almost done, resolution zoom. And this one was fun. So this is a WebGL game I've been building with, so I've been working in the past on the WebGL engine named Babylon.js, and now I've been a stupid WebGL game. And you see that I'm currently having 33 watts being used. If I'm, zooming, increasing the zooming level to 400%, I'm lowering down the number of watts being used. You see that it could up to 50 watts, and now I'm going to go back in history, and the more resolution I'm generating, so what the zoom level is doing in my case on my WebGL canvas is going to modify the internal rendering resolution. So this is something a lot of games are doing. If you have a 4K screen, if it's too complex to render a 4K image, you're going to render a full HD image, for instance, and do an upscaling of it. This is exactly what the zoom is doing on the browser, and it was fun to see that lowering down the resolution, internal resolution, was directly impacting the energy being shown on the watt meter. So it means that, once again, an easy way to lower down the energy is to reduce the resolution being used for your canvases. So it could be 2D canvases or WebGL canvases. Maybe it will be a little bit more pixelized on the screen, but then you will use less energy. At last, service workers. So this one was more difficult to evaluate. So my game, I don't know if I can show you my games, but my game is super simple. So I can launch it. And you see, you've got this loading phase when I'm going to load some resources, and when it's ready, it's going to switch to the main game. And this is my stupid game. So I wanted to evaluate how to optimize this specific part using service workers. So I don't want to measure the energy spent by the WebGL rendering, so just the loading phase. So during the very first launch, the Power CFG, so Power CFG can tell you the total number of energy used, and then on the CPU, on the network, on the various interesting parts. So it took 22 joules to use the network stack to load my content. And during the full sequence, it took 423 joules, because it takes much time to load the data from the network. But then I've got my spinning, loading, a logo that's going to consume, in fact, much more energy than the network stack itself, because it's going to use already the GPU and the CPU. So the longer the loading sequence is, the higher energy you're going to consume, not because of the network, but because of the display itself. So once everything was in cache, the network stack was almost at zero because you always like a bit of HTML and CSS to download. So I mean that the launching sequence was much more efficient when everything was in the cache. But I haven't really optimized the network usage because I've been able to reduce the launcher time rather than optimizing a lot the energy because of the network. So we've been doing something else. We've got like a small sample application with some DRM content. We wanted to test if PWA was able to display offline DRM content. So we've been using this famous free video. And so what I've been doing, I've been using this PWA and measuring, like playing 2 minutes of DRM content while I was online. And the total number of energy being used during those 2 minutes was almost 500 joules, with only 31 joules being used just by the network. Playing the same 2-minute video in airplane mode, so without the network stack enabled, I've been able to save 12% of energy thanks to the service worker. So in conclusion, it means that we can have some impact of energy on the CPU level thanks to WebAssembly in certain cases, thanks to web workers sometimes. Changing the colors or black theme, white theme doesn't going to change a lot. And service worker can help a lot on saving some energy on the network stack. Plus, it's going to save also some energy on the network infrastructure and the server itself, where all your data are stored. So service worker is maybe one of the most interesting technology that we can use in PWA today. So some idea for the future, because I didn't have the time to test it. I don't know if SVG images, for instance, are more efficient than bitmap or big images compared to small images, or using lazy loading. Is the fact that using lazy loading is more efficient? I'm not sure, because then you need maybe to do, I don't know, more network requests rather than a big network request. I don't know. I would need to measure that. I don't know if you've got idea on your side. I was thinking maybe also about adapting dynamically the behavior of my web app by based on where I'm currently based, using the map we've seen at the beginning. So let's say that this PWA is being currently run in France. We know that it's more efficient on the carbon level. Maybe I can do more network requests compared to being hosted in Germany, or maybe I can use more often the service worker in Germany rather than France. So maybe it's a stupid idea, but something I was thinking about. Using the battery APIs to this time propose a kind of efficient design. It could be a sustainable design. So maybe avoiding auto-launching videos, maybe trying to lower down automatically the type of quality video to be used based on the current level of API, because I can know that I'm almost have no more battery. And then I like to check if it would be possible to create some CSS, maybe framework or JS framework to help people building sustainable PWA. So for CSS, I'm not convinced, because CSS is a lot on the rendering of the image. But sometimes CSS can also use GPU based on the way that you're going to define your CSS. It will be either computed on the CPU or GPU. So maybe we can build some CSS frameworks that are more energy efficient. This is something I haven't been able to check. And I've stopped there. So now I can thank you for listening while I try to do while benchmarking PWAs. And I think we can have questions, but I'm not sure.
Okay, Davey, thank you very much. So we don't have much time for questions. I just have one thing to say. I heard it's your birthday today, so happy birthday.
Thank you.
Yeah, we don't have time for questions, but if you can go on the YouTube chat, and there's some people who ask questions, so if you have a few minutes, that would be great if you can answer them. And so we will set up the next speaker in the meantime. Remember to go get your Azure Hero badge. Try to win the Fairphone with the raffle, and we'll see you in just a few minutes. Thank you, David, again.
Thank you all.
Hello, and we are back. So I am back with Sara, and we're going to speak about machine learning, and the idea will be to know if machine learning can be sustainable. Before we start, I have just a little question for you, Sara. So someone told me that you've been doing quite a lot of gardening recently. Can you tell me a little bit more about it?
Yeah, sure, Maud. Yeah, so everyone needs a quarantine project, I suppose, and I decided to plant chilies. I didn't expect all of them to grow, but they all did. So basically, my entire balcony and all of my windows are just filled with chilies, and we still have chilies like hanging and drying everywhere in the apartment because there was no way we could eat them all while they were fresh.
Nice. Excellent. So if you're ready, I am ready as well, and we can launch your talk.
Awesome. Thank you so much. Thanks, everyone, and hi. It's awesome to be here speaking to you in these strange times. Who am I? My name is Sara Bergman. I am a software engineer at Microsoft at the development center here in Oslo, Norway. I'm actually Swedish, but I realize that is a distinction which may only be important to Scandinavians, but I saw there were a few fellow Scandinavians in the chat, so shout out to you. In my day-to-day job, I work in a team under People Services, and we own a set of APIs for profile data and profile images within Microsoft 365 and sort of beyond that as well. This is my fourth conference online. It's getting a bit less weird every time. Although the strangest things is not being able to see anyone, to just have like a screen. But I used to be a dancer, and when you're a dancer on stage, you have this really bright stage light in your eyes, so you don't necessarily see anyone then either. So I try to see the laptop as my stage light. All right, enough about me and back to what we're actually going to talk about today. Is machine learning sustainable? When we talk about sustainability and machine learning or AI, or really within the entire computer science field, we talk a lot about the computational need first. And the second part we sort of think about is maybe improving hardware. And as for hardware, it has truly been an enabler of both machine learning and AI, as AI has been an idea for like a long time, ever since Turing's article back in the 50s. But it's only recently that it's been infused in products and services that we see and use every day. So yes, if we can make hardware greener or only running hardware on greener energy, then machine learning can be a lot more sustainable. But is that enough? As we saw in Asim's talk, who was first, likely no. But that is the portion I'm attempting to dive deeper into on these next half an hour, 40 minutes or so. And I will take you with me on that ride. I will talk a bit about why this is important first. And then I will talk a bit about how we can measure carbon cost, how we can go from like a piece of code to like a value in CO2 that we can reason over. And then there will be a lot about research from the fields. I will cover papers and blog posts and some master theses, which try to point out the connection between energy consumption and accuracy for machine learning, as well as the connection between the amount of compute or work done and energy consumption. And then lastly, I will finish up with covering what you can do if you're someone who writes machine learning code every day, but you don't necessarily know all that much about data centers. What can you do? Okay, let's jump right in. So why should we care if machine learning is sustainable? I think the first reason is obvious. The world confronts an urban carbon problem, and if we don't curb emissions and temperatures continue to climb, science tells us that the results will be catastrophic. Doesn't sound nice at all, so let's try and avoid that. As to how important the ICT sector is in comparison to other sectors, there isn't like a ton of new research. The most cited paper when you read other research papers is from 2010, And that one puts the ICT sector at around 2% of worldwide greenhouse gas emissions. And that is actually on par with the aviation sector, which when I first heard this, I found it quite ironic because we talk a lot about flying and if that is green or not green, but we rarely discuss the impact of me watching Netflix on my couch or surfing on Instagram on my phone. There is more research from Europe from 2015, and they put the ICT sector as responsible for 4% of the European greenhouse gas emissions. We have to remember here that in Europe, we don't have as much manufacturing maybe as other parts of the world, which traditionally has a big chunk of those emissions. So yeah, the exact numbers are not clear. What is clear is that they're non-negligible and we need to act, and we have the opportunity to act. The second part, which perhaps may be less obvious, is to democratize AI. If AI is really computationally heavy, it raises the barriers for who can do it. It basically limits this to companies, maybe universities, and one or two people who have the resources to do this type of groundbreaking research, which in the end limits everyone as research in the entire field is blocked. So how can you measure the carbon cost of your machine learning solution? You start typically by measuring the electricity. This is something that's been covered in David's talk, who was just before me, and also Asim, who was in the keynote. And this is done perhaps most easily by buying a watt meter, which you plug into a wall, and then you plug in your server or your laptop, and you start from there. You can also use different types of built-in tools to get a number on how much electricity you consume. There are some caveats to be aware of. It's not super simple, but it can definitely be done. But it's not always that you have, maybe you run in the cloud, for example. It's very hard to sort of knock on the door of a data center, like, can I just plug in my watt meter here? Likely that's not going to end well for you, so I don't endorse that. What you will then have to do is to estimate the electricity. And you can do this in a rather scientific way, which we will talk a bit about later in the presentation as well. But it can be done based on things you can actually measure, and then based on that, you can estimate. So now you have the electricity. How do you convert that to a carbon cost? You need the carbon intensity. This has also been covered a bit previously today, but basically the CO2 equivalent, which is sort of what we talk a lot about, and that is one value that we use that we can convert all different greenhouse gases into like one single number. This makes it a lot easier to compare and reason over. For example, if I have 1 kilo of methane, that has the same global warming potential as like 84 kilos of CO2, but then it lasts a shorter time in the atmosphere compared to CO2, so that also takes effect. And already here, my high school chemistry is not enough to follow anymore. So this is very complex. That's why we need a simpler way that everyone who's not an expert in chemistry can understand. And that's why we use CO2 equivalents. And how do we get to those CO2 equivalents? Yes, electricity always has a cost. Depending on where you are, the cost is going to be higher or lower. For example, I'm in Norway right now, where we have like 98 or 99% hydro. Hydro is also very nice because it runs in the day and in the night, as long as it rains, and it rains a lot here, so we have a lot of hydro. Many people before me have shared the electricity map, and Norway is usually below 30 grams, so it's pretty good. We're also exporting a lot. But if I were to sit in a different country, who like Poland, for example, who burns a lot of coal, then the carbon intensity would be higher. So those are the two sort of main components when it comes to carbon cost. Okay, so what should we be comparing? As you know, depending on how you twist and turn your data, you can support different claims and paint different pictures. And I will use 2 different blog posts from the OpenAI blog to demonstrate what I mean. And those examples here will be on convolutional neural networks. What we could do is to compare the performance of different algorithms on the same data set with the same accuracy goal over time, and that will be the efficiency of AI. Or we could compare state-of-the-art to state-of-the-art algorithms from different points in time and look at how the computational need have changed over time. Sounds a bit complex? Let's break it down with a few examples. We start with the first one, which is efficiency over time. So here's a really cool graph. It's a lot of information, so let's try and break down the axes and then talk about what it actually shows. So it has years on the x-axis from 2012 to this year, and it has teraflop days on the y-axis. Flops is floating point operations, and you can think about it as a way to denote work that the CPU does. The whole graph is also in log scale. And what this graph shows, or what they did when they did this experiment, was to measure the amount of compute that was needed to train a convolutional neural network on a data set called ImageNet, and then classify this to the same accuracy as AlexNet, which you can see as their starting point on the left. And basically what they did is to keep the performance of the system constant. And then they used open source re-implementations of publications of neural networks and measured the progress of this ImageNet data source over time. And this research only focuses on the final training cost of an already optimized model. So the development of this model is not included here. And what we see here with this graph is that since 2012, the amount of compute that is needed for this same task, essentially, has been decreasing by a factor 2 every 16 months. So compared to 2012, it now takes 44 times less compute to train a neural network to the level of AlexNet. And we talked about hardware in the beginning, so let's compare it to classic hardware efficiency and Moore's law. If we have Moore's law during the same time period, we will get an 11-time cost improvement, which is significantly less. So that's very interesting. This proves that algorithmic progress in this area have yielded more gains than classic hardware efficiency, and it may continue to do so over time. It also paints like a really nice picture when we talk about carbon emissions and sustainability. We like it when graphs point downwards, and that's generally very nice. But we know that there is a strong focus within the machine learning community to obtain these state-of-the-art results. You can see this by there's a lot of like popular leaderboards, and they typically report accuracy as a measure or similar metrics, but they don't really have any mention of cost or efficiency of their solution. So while the last graph is really interesting, it is likely not the biggest driver of carbon emissions in the area. Okay, so what if we look at the second example? What happens if we compare state-of-the-art algorithms to each other and look at how the need for compute have changed over time? More graphs. Okay, let's do the same here and break down the axes so we understand what we're looking at. This graph also has years on the x-axis, but it's an older blog post, so it only goes until 2018. On the y-axis, we have petaflop days instead. And if you're thinking a lot about prefixes, I can tell you that a petaflop is around 1,000 times a teraflop. This graph is also in log scale. And what they did here is to show the amount of compute that was used in the largest AI training rounds. And the criteria for how they choose these models were threefold. So the selected results should be relatively well known, and they should use a lot of compute for their time, right? That's where the state of the art comes into play. And then, of course, give enough information so that they could actually estimate the compute needed. And then they measured the amount of compute, again, to train a single model. No development cost here either. And they chose this in both examples because they believe this number is most likely to correlate to how powerful our best models are. So what does this graph show us then? This shows that since 2012, the amount of compute used for these very large training runs have been increasing exponentially with a 3.4-month doubling time, which is quite fast. If we compare to classic hardware again and Moore's law, that would have that has a 2-year doubling period. That's a significant difference. So since 2012, this metric has grown more than 300,000x, and a 2-year doubling time would be like 7x. So this is quite a big difference. And it has largely been supported by more and better and more expensive hardware. For example, the use of GPUs and the increased parallelization we do. And better hardware will continue to have this accelerating effect on machine learning and AI. But on the other hand, the authors of this blog post argued that the cost will eventually limit how much we can do parallelization, and physics will eventually limit how efficient we can make our chips. So in conclusion, this trend will likely not go on forever, but it is likely that it will continue in the same manner, at least in the short time frame. So this is super interesting, I think. The graph is less pretty though, and since we know that the carbon footprint is tightly coupled with the compute needed, this is an indication that machine learning may not be the greenest field we have in computer science. Okay, so by now, a lot of people are maybe thinking, what about all the good AI and machine learning can do for the environment? Can't we use it to decrease the impact of global warming, help us estimate the carbon intensity, or all these other things? Yes, completely with you there. I am not saying we should stop using all this great tech, because after all, the most carbon efficient software program was the one that was never written, but that's not what we're trying to do here. I'm also an engineer. I also like writing software. What I am saying, however, is that without this core stone knowledge of how to measure the sustainability of machine learning, we can't even start to reason over the rest. What we need to be asking ourselves are things like, how much carbon can I spend on developing my model before the cost of development is actually higher than the carbon savings? Or how long do I have to use these carbon-saving AI solution until I've paid off that carbon depth of development? And what is actually sufficient accuracy for this task? And how much carbon am I willing to pay for that? What are our options to minimize this impact? These are the sort of things we need to be starting to think about and starting to reason over. But one great example of how we can use machine learning for good, I choose an example that was close to home, Expressen. It's a newspaper article in Sweden, and they still deliver newspapers to, I think it was 6,000 locations or something like that. Newspapers are very time critical, right? They're only really relevant on one day. So they started using machine learning to predict how many newspapers they should deliver to which place. And one of the effects that they measured or noticed was that they had fewer papers returned back to them. And that leads to less waste. I mean, it's awesome if we can recycle things, obviously, but it's even better if we can stop things being produced that are never going to be used. So I found that to be a very good example. Okay, we're gonna look at some more research now. This is a paper by Struble and a few other people, and it is heavily cited. What they did in this paper, which was one of the first, I believe, in this space at least, was that they characterized the dollar cost and carbon emissions of deep learning and natural language processing. So they did this in two parts. The first part was to calculate the dollar cost and the carbon emissions for training a variety of popular sort of off-the-shelf NLP models. And the second part of the paper was a case study to estimate the resources that were required to transfer an already existing model to a new task, or more the development cost. So how do we get to that? Well, they estimated the kilowatts of energy required to run this training, and then they converted these kilowatts into approximate carbon emissions and electricity costs. And that generates a bunch of numbers. And in order for us to understand what's behind those numbers, I think we're going to have to walk through the math together. So the first equation you see here is how we get carbon dioxide equivalents. So we take the power that was actually used for a task, and then we multiply that with something called the power usage effectiveness. This is a ratio which tells you how efficiently a data center uses energy. It's basically like how much energy is used for actual computing equipment compared to waste and cooling. And that's the first magic number here, 1.58, which is what they used in this paper. And that was the 2018 global average for data centers. And this basically means that 0.58 units of energy was wasted on non-compute tasks. And the goal is a power usage effectiveness of 1. And many data centers are actually heading in that direction. Okay, so that was the two first parts. The second part is the carbon intensity, which has already been touched upon quite a lot. I'm just going to mention the magic number they used here, which was 0.954 pounds. We've been using grams a lot in this conference so far, but now we're going into US research, and then we're using pounds. And this was also the US average for 2018. So how did they measure power? They actually estimated it, but also measured it, but they didn't measure with like a watt meter. What they did is they measured the average power drawn from the CPU, the DRAM, and the GPU times the number of GPUs. And because those are going to be the main offenders, at least the CPU and the GPU are going to be the high spenders here. Okay, that was all of the math. Let's look to their actual results. So this was the first part, which was to calculate the dollar cost and the carbon emissions for those popular off-the-shelf NLP models. So there are two graphs here. The graph on the left is sort of just some average everyday examples for CO2 equivalents, because at least like that number doesn't say me anything. I need to compare it to something to understand what it means. So that's the graph on the left. The graph on the right on the other side is their results. So they have their 4 models, which is Transformer, Elmo, BERT, and GPT-2. And the column to the almost furthest right is the CO2 equivalents. And as we can see here, just training those models comes with a quite significant cost. For example, BERT is almost the same cost as a trans-American flight, which is quite a lot. NAS, on the other hand, which is the transformer, but they did the neural architecture search, that is 5 times a car lifetime. And that is a lot for just training. So this was the first part. The second part was to do a case study to estimate the resources required to transfer an existing model to a new task or develop new models. And this cost is going to be even higher than only training the models. So what they did here was to study the logs for the training of development a specific NLP model. The graph to the left is the same as before, just some everyday examples. And they only had the cost for this. They didn't actually publish the CO2, which was a bummer, but it's tightly correlated to the cost anyway, so it's still interesting to see. And what this paper shows here, like the graph to the right, is first the cost of training a single model, then a single tune, and then all of the models. It's a quite steep increase there. So in all, what should be our key takeaway from this paper is that the training an NLP model and developing new ones, it has a significant cost for the environment in terms of CO2. All right. So the next paper is not actually a paper, but a master thesis, where they aim to find a methodology for a fair evaluation of machine learning algorithms with respect to resource consumption. Because as we talked about in the beginning, many times research only publish their accuracy and that type of data, not necessarily the resource consumption. And this is also not a peer-reviewed paper, so the exact numbers aren't the most interesting, but the general trends is what we're interested in here. And what they did was they used 3 different image data sets and 3 different text data sets, and then compared 3 different machine learning modules. They used CNN and MLP, which are neural networks, and then SVM, which is a very simple machine learning algorithm. And what they did was to contrast the accuracy of these models with the training energy. So they actually measured the energy cost of the CPU and the GPU, which are the main offenders, and produced these results. So the number after the model here is going to be the number of epochs they run it for. And then we have training energy on the y-axis and accuracy on the x-axis. And what we see here is that for relatively little increase in accuracy, we pay a rather high cost in training energy. So it's quite expensive to move a few points up the right side of the graph, sort of. You also go very high. And we will see this in the next paper as well. So this is a paper called Green AI. And this is a peer-reviewed published paper. And they proposed making efficiency and evaluation criterion for research alongside with accuracy and related measures. So it's very similar to the one we just looked at. But this one is a bit more extensive. And what they also did was to divide AI into 2 different branches of AI. So they called one of them Green AI. And Green AI is research which yields novel results without increasing the computational cost, and ideally even reducing the computational cost. And then they also have Red AI, which is research that seek to obtain state-of-the-art results in accuracy or other related measures by using massive computational power. And Red AI is sort of what we normally think about when we think about AI research, but they argue that Green AI is also more democratic, as we mentioned in the start of this talk. They basically want anyone with a laptop to be able to do Green AI research. So what they did here is they didn't measure, but they suggested a completely new metric, or not completely new, but they suggested a metric, which is floating point operations, FLOPs or FPO, as this concrete measure. And FPOs is the total number of floating operations that was required to generate a result. And FPO is really good because it provides an estimate for the amount of work that you need to perform for a computational process. And it also is very correlated to the time you need to run it. So therefore, it's also good. If this is the first time you hear about the floating point operation, no need to be confused. You can think of it as a way to characterize what your CPU is doing. Like you can define a cost in floating points for like basic CPU operations, and then from these basic CPU operations, you can like derive the cost of like more complex tasks your CPU does. And it's good because that's going to transfer between platform, that's going to transfer between softwares. It's really a good way to compare different things because it's like this small common divider. Or yeah. All right, so let's look at some dashboards. They used existing metrics to showcase how this metric could look like. So we have 2 sets of graph. The graph set to the left is very similar to one of the first blog posts we looked at, which is basically different models from different years. And then the one to the right is one model, but all the different layers. And the top graph is the accuracy. the two red ones. And then in the middle, they have this new metric, floating point operations in billions. And then the bottom graph is the number of parameters in millions. And I found this really interesting because what I found most interesting is how accuracy ties into computational cost. If we look at the graph to the right, we see that we increase like 1 percentage point from 77.4 to 78.4 in accuracy. And for that, we almost double the number of floating point operations. And it's like a big difference in the amount of compute we need to do, and therefore the amount of electricity, and therefore the amount of carbon we emit, just to get that little bonus in accuracy. It's very similar to the left graph. After we come above 78% accuracy, like you don't have a huge impact in accuracy, but the floating point operation is like continuously going up. So that was very interesting, I think, the first time I saw it. And that was all of the research. Good work for making it through. I know it can sometimes be very dusty, but now we're done with the research, and let's summarize and look at what you can do instead. So what we've learned from all these papers is that machine learning comes with a significant compute cost. And we know that this compute cost translates into a significant carbon cost. And there are also indications that this is getting worse over time rather than better with time. But there is light on the horizon. We have seen that the efficiency of machine learning is getting better. We are literally getting more bang for less bucks if we can settle for less than state-of-the-art accuracy. There are also more and more research in this field, and this question is being asked and answered a lot more now compared to just a few years ago. So what can you do? Reduce, reuse, recycle is something that we talk a lot about in waste management. I hope you heard it. And it can actually be used here as well. My dad used to work in waste management, so I know there are more things you can do besides recycling, but I didn't have a good analogy for how you could burn your code to heat houses. So I'm going to stick to these three. Okay. The first thing you can do is reduce. So you can reduce your accuracy hunger. What do you actually need for this task? What's the accuracy that is sufficient for what you're trying to achieve? And how much carbon are you willing to pay for that? Here you also have to think about the risk, obviously. Some things you can't safely decrease the accuracy because there is risk to maybe humans or machines or something that you're not willing to sacrifice. That's okay. But for other things, maybe you can safely decrease the accuracy for like a recommendation service of some sort. Yeah, you might see increased sales if you recommend that little bit better, but this also correlates like an electricity bill. If you have to double the amount of work you do for that little increase in sales, like will it even break even in terms of cost? Like those are the things we need to start to think about. You can also reduce your carbon intensity. That's sort of the second part. The first part is like, how can I do less? Use less electricity, and the second is how can I make sure that the electricity I use make the least amount of impact, and that you can do by reducing the carbon intensity. You can plan the training of your models, like when and where you run them. For example, we know that there are some times when the grid is going to be really choked. Like when everyone is starting the washing machine in the morning and using the shower and all those things, maybe that's not the good point. Maybe it's another point in time. You can also reuse other people's models. You think about other open source models available, and that way can you like cut out the development cost and only, in parentheses, pay for the training cost of your model. And then pay that forward as well. Are you able to publish your work as open source to sort of let your development cost be worth something for others as well? And thirdly, you can recycle your own machine learning and AI solutions for new problems. Maybe they don't fit for type A problem anymore, but maybe they're super great for type B, and therefore, again, not pay that development cost. All right. Thank you so much for listening. Now I believe I have time for some questions.
Yes, thank you very much for your talk. We have several questions that were asked on YouTube and on Twitch as well. First question by Asim. What has driven the desire for energy efficiency in AI, in your opinion?
That's a good question. So I think historically, one of the reasons we haven't been able to do a lot of AI is because it's been very expensive, because it requires a lot usually. So now we're able to do it because we have, like, hardware has given us those tools, but we're also realizing it's still expensive. So I think that's also good, like when we decrease the energy usage or become more efficient, we also decrease the cost. And decreasing cost is something that your company will never say no to. So if you're wanting to do this, and yeah, I think cost is always a good way to any manager's heart.
Thank you. Thank you very much for this answer. Then another question. So how can we help in saving the environment and reducing climate change as a software development?
Good question. I think the first thing is just becoming aware that you can actually have an impact. And then secondly, you're going to have to identify what in my service or my application is the one that consuming power. So what is consuming power, and can I make that less? And if you consume less energy, you are going to decrease the amount of carbon you're releasing, or carbon equivalent you're releasing into the environment. So that is like one thing that is maybe the first stepping stone, and then you can continue on that path. Okay, can I like run my servers hotter, for example, like less idle time? And what can I make sure that the client, if you are like a user-facing application, how can I make sure that the energy spent on their side, like on their phone or on their laptop, is as small as possible, so they don't have to like charge their laptop all the time? Because you can really control what energy you use on your side, on the back-end side, but on the front end, you can't really do that. You have to rely on what they have. So making sure decreasing the energy both on your side and on the client side, I think, is a good first step.
Thank you. And we have another question by Asim, who asked you your first question. This question needs maybe a little bit of context. I hope you can remember what you got to.
Yeah. So I believe, let's see if I can go back to that slide.
I will just read the question again in case someone needs reading. So a 16 times increase in efficiency, but a 300,000 times increase in use?
Yes, so I believe this is what he is referring to. Basically, yeah, that's the thing. Accuracy has gone up with these AI models, but we are using a lot more compute. This is for very large training runs. I'm not sure about the 16 time, because I don't think they actually had how much better these are compared to these. What we can say is for this, basically, the accuracy is the same. For these, I'm not sure they published how much better these were than these down here. But it's not like you can't become 300,000x more accurate because you started pretty high already. So yeah, you pay a lot for not that much better results, in my opinion.
Okay, thank you very much for these replies. So this is it for this talk, and we are going to move on to a very short break in a second. And after this, we'll meet with Jen Looper, who is going to speak about becoming a green developer. Thank you, and see you in a minute.
Hello.
Hello.
Hi, Jen. How are you doing?
Good, thank you.
So I just installed TikTok for you, you know, like 5 minutes ago. Because I heard that you are JavaScript auntie.
I am JavaScript auntie on TikTok, that's right. So
So
I need to
what do you post there? Can you tell us?
say it again, sorry.
What kind of video do you do?
Oh, it's a social experiment. I'm trying to figure out how to teach JavaScript basics on TikTok. And these videos are 60 seconds. So it's really challenging. It took me I don't know, like an hour to build my last one, which has a lot of screenshots. And now I'm trying to figure this out. It's very interesting.
I can see that you already have 6 videos. So yeah, I encourage people to go, if you have TikTok, just search for JavaScript auntie and you will find Jen.
Good fun.
Okay, Jen, so you're going to talk about how to become a green developer. So I won't take much of your time and see you after for the questions.
Okay. Great. All right, I'm going to share my screen here. I hope you can all see it and hear me. So hello, everyone. I'm joining you live today from my office. I retrofitted my closet into an office, and I'm in Boston, where it's a dark and stormy morning. So I'm here to talk to you today about becoming a green developer. I really enjoyed the last talk by the last speaker, and this in a way builds on that idea that she had at the end of her talk of, maybe we could create a tool that would help us to make green decisions on when to do things, for example, when to train your fancy and very accurate machine learning model. So let's go ahead and get started. My name is Jen Looper. I'm a cloud developer advocate at Microsoft, so I'm happy to be here. So what's on the agenda today? Today we're going to learn about sustainable software development, and then we're going to all code together. So I hope you're excited. I love coding together. It's super fun. All right. So what is sustainable software development? Well, it's an emerging discipline at the intersection of climate science, at best practices of software development and software architecture, at figuring out how electricity markets work and how all of this applies to your profession as a software developer, to figuring out how hardware and data center design all fits into this puzzle that we're trying to figure out. And I would just refer you to a website you've probably already visited. My colleague Asim is in charge of this website. It's called principles.green. Take a good look at it. There are 8 principles that you can follow to become a little bit more green in your profession as a software developer. So the goals of this talk is to shed light on how we can follow certain recommendations to become that sustainable software engineer, and how you can make specific green decisions that can have this nice and meaningful impact on the carbon impact of your applications. And once again, check principles.green for these 8 recommendations. I don't have time to go over each one of them, but a couple of things that we're going to do today touch on some of those recommendations. So when I was working on this talk, I was trying to just ask myself this question: is it possible to build a carbon-friendly app? We're engineers. I'm American. I don't really ascribe to the Silicon Valley mantra that we can engineer ourselves out of everything, but it is this kind of idea that we as builders, we can build something that will make things better. But sometimes I just wonder, should we be doing that? Should we be building that fresh greenfielded website? Should we launch that extra mobile app that will help us, make greener decisions? Should we build a desktop app? What's the activity that we should actually be focusing on? And the problem I kept kind of bumping my head into was that, building fresh web assets that are always online consume unnecessary energy to keep them live. And I was trying to figure out some solutions to this. What about something like cloud hosting that can help you spin up assets when they're requested and they're needed? Or you could go for an offline first strategy that can keep energy requests low. I work for Microsoft, so we have our cloud solution, Azure, and other clouds that allow you to, spin up things and spin them down when you're not needing them. So that's very helpful. But maybe there's even a better solution for some of our use cases. Not every use case, but maybe some of our use cases. And the solution I kind of stumbled upon was that, what if we just build something that's hosted locally? We're just going to build this for ourselves. And by doing that, it can answer several principles. And some of it can answer 4 of the 8 principles, which I kind of outlined here. So it could answer this idea that, maybe we could build applications that are carbon efficient, and we can build an application that's energy efficient, just by the architecture of the application. We could reduce the amount of data and the distance it must travel across the network by not building something that's online all the time, and by not building something that's pinging constantly to check for fresh data. And then this idea that instead of shaping supply to meet demand, we might try shaping demand to match the supply. So this extension that we're going to build, spoiler alert, we're going to build a browser extension, can help you, especially with number 7 here. Instead of shaping the supply to meet the demand, we're going to kind of figure out what our demand is and how it might match the supply of energy that's out there. So something kind of fun to try. Okay, so we decided we're going to build a green browser extension. Well, what the heck's a green browser extension? It can do 4 things. So this browser extension is going to help you make educated decisions to manage your personal energy usage choices. So it's going to say, okay, I live in this region. This is the carbon intensity of my current region's usage. This is what's going on in my region. And maybe I can figure out, what the task is that I need to do. And then I can figure out whether it's a good time or a good moment to do that task. This extension is hosted locally. It's just a little extension in your browser that's looking at your locally built app. And we're calling it ad hoc. So you could make it so that it would be pinging constantly to check an API, to check on the carbon intensity of your region. But I figured, well, I really don't care at 1 in the morning, I'm sleeping. So why don't we just do it so that we call it ad hoc and get our reading and then make the decision that we need to make at that time. And then I decided we'll just build with vanilla JavaScript. So there's no framework overhead. There's nothing on top really that's going on. It's a very simple little app, simple but powerful. That's what we're going for. Now, when I was getting excited about browser extensions, my colleague said, hold on, not all browser extensions are created equal. And he gave me a nice screenshot here of an Edge extension here that is just crushing his machine, because I think it's a password manager and it's pinging constantly. There's that problem again, and there must be some kind of memory leak going on. So he always has trouble with this extension sucking up a lot of juice. So that's not the extension we're going to build. We're going to build something a little bit simpler and a little bit less pingy. So this is something that the previous speaker said, which is a luxurious point of view, but in this case, it's valid that the greenest app is actually the one you don't build and the one you don't particularly, post into production, but just something you build for yourself to help yourself make green decisions. This is what we're going to build. This is what it looks like. It's our little browser extension. It works in Edge, Chrome, Firefox, and I cannot figure out how to add a browser extension into Safari, but I'm going to guess that if you can figure it out, it will work. Ping me on Twitter at JenLooper if you can make Safari behave itself. So this is what it looks like. And what you're going to do is you're going to input your region's code and your API key, and you're going to get a reading. And then there's the little dot here at the top that shows you the reading of your region, and the color will change according to the carbon intensity of your region. So the API that we're going to use to query is the CO2 signal API, and it changes the color of the icon, like I said, based on the carbon intensity in your region. So green is better than red, for example, which you can see. I'll do the demo in just a second, but you can see New England is always a little bit yellow and red. I don't know what's going on, but now we need to educate ourselves. And then you'll be able to get a quick readout of your region's carbon status. And thus, knowledge is power. You can save power by gaining knowledge, right? Okay. So here's the demo. I'll just pop it up in Edge. Like I said, it also works in Chrome. So I've already input my region, which is US NEISO. My carbon usage is a little high, but I think what really kills us in New England is that the fossil fuel percentage, the percentage of energy, the percentage of fossil fuels used to generate the electricity is pretty high. That's not great. And it's a little surprising to me considering that we have some big wind power projects and supposedly we're a little bit more green as a region. But like I said, knowledge is power. So now we can, have some data to show our local legislatures, for example, saying, what the heck's going on and why is the wind project not happening? So lots of information that you can get from this kind of thing. Okay, so now I'd like everybody to please follow JavaScript Auntie and open your computers and navigate to this GitHub repo. It's github.com/jlooper, carbon-trigger-extension, and go to the start branch. So what I've done is I've created a couple branches. I've created main and start is incomplete, but by the end of this talk, you're going to have this complete solution. When you have that forked, make sure you're using start, and then navigate to the root and do npm I to npm install your dependencies. This is assuming that you have npm on your computer. So maybe now's not the time to reconfigure your computer for this, but if you want to take a look at this after the talk, this is how you would do it, and everything's in the README. And then take a look at the files. So we have, let me just make this a little smaller. Here's where it gets dicey because I want to show a couple things on the screen. Okay, so this is actually the main branch, which is all built. So I'll show what this is going to look like. So we have a couple folders here. We have our distribution folder, our dist folder, and that's what happens when you use Webpack to build your extension. Everything gets built into dist, but you do edit a couple files in dist, which is kind of interesting. The file that's actually built is this main.js file. So that's obviously a built file, but everything else you're going to be editing. In the source folder, that's where you're writing your main JavaScript. And this is mostly what we're going to be editing in this talk. So you have, in the dist file, you have a manifest folder, or manifest JSON file, excuse me, with some information about your extension. In source, what I was just showing you, the source folder, you have this index.js file. That's where your JavaScript code is going. And then in dist, in the dist folder in index.html, this is your HTML markup. So this is where you saw that image and, my carbon trigger. Welcome to your personal carbon trigger. In the background file here, there's some background tasks that are happening. So when icons are changed, this is all happening as a background task. I borrowed this idea from the Energy Lollipop extension, actually a nice extension if you live in California. I'm in Massachusetts. It doesn't do me any good, but very, very nice solution. And then dist and index, that's a mistake. The main.js file in dist is where everything is being built by Webpack. Okay, so what's the development process for building a browser extension? Before this talk, I had never built a browser extension. It's really fun, and I want to do more. You basically are building up a JavaScript app, and then you're using npm run build to build it using Webpack, and then you add your extension to Edge. So if I open up Edge, you can see that if you click on these little dots here, you see this extensions page right here. You go there, and then you can go ahead and load unpacked any built extension that you are wanting to experiment. So this is how you develop locally and test, and you can always either remove it or reload it. You can even inspect your background page. That's really nice, and then you can always find new extensions if you decide to publish your extension, which maybe we should do. Okay, so what we're going to do is you're going to work with me on the start branch, and we're going to complete the code. But before you do that, I would like you to go to electricitymap.org and take a look at the map, how it looks. And then I want you to grab an API key for your extension. The way you do that is you go to co2signal.com. And it's kind of weird. It's like you put in your email address and then they email you an API key, but it happens pretty quickly. So go ahead and do that. Grab your API key, and then go to and all of this is on the README, by the way, of this repo. Go to the electricitymap.org API page and take a look at the zones, and you'll see which zone is closest to you. I have a couple, but I have had the best luck with USNE ISO, New England ISO. And there's plenty of zones in Europe, and you can grab yours. I know for a fact that FR is France, so I'll save you the shortcut there. And FR always is green in your icon, so good job, France. Okay. All right. Are you ready? Let's go ahead and open up our code base. So I'm going to go ahead and switch to start. And what I want you to do is follow the bouncing leaves. So the first thing we're going to do is go to source index, which is here, and we're going to look for number 1. So there's some numbers in here, and what I've done for you is I've created snippets. It's in the snippets folder, and you can just type 1 and then hit 1 and hit return, and that will give you a snippet that will just allow you to copy the code so that we're not messing up typing. So number 1 is just allowing you to check if anything is in local storage, you're going to grab that. So what we're doing is we're saving our API key and our region name in local storage. So that's the first thing. We're just going to grab that if it's available. And then what we need to do is manage the local storage inputs that are input via a form. So we're going to take a look at the setup user method, and you're going to set the user entered API key and your region. So let's look for number 2. Where's number 2? Here it is. 2 and return. So here we are setting the API key. So it's calling setup user, passing through the API key and the region name that you're entering in the form, and setting that in local storage. Your browser extension has its own little local storage. It's quite interesting. Nice little architecture. Then we're ready. Once we're set up with our local storage API key and region name, we're going to go ahead and make that initial call right here in setup user. So let's make the initial call, 3, to call display carbon usage and pass through the API key and the region name. So we'll go up to, so this is the method display carbon usage. And you can see we're passing through all the information, and we're using Axios to go ahead and query the API. All right, halfway's done. So the fourth thing we're going to do is we're going to display our usage and carbon source as it's returned from the API. So we're going to go ahead and click 4. And this is where you saw that text saying, that what we're looking at grams of CO2 emitted per kilowatt hour and the percentage of fossil fuels that is being used. So that is your display. Once you get the response, you display the information. 5, we're going to set the icon to be generic green. Now we're going to start some icon manipulation. So let's go ahead and also still in source index, we're going to look for 5. Where's 5? Right here. It's in the init, which you call asynchronously. So 5. So here's where we're going to use Chrome's runtime methods to send a message. So remember, Edge is built on Chromium. So we're going to go ahead and send a message to Chrome's runtime to update its icon. And we're going to set it to green initially. Okay. And then we're going to calculate the color of the icon based on the carbon intensity. So this is number 6. So number 6, we're going to start with green, and then we're going to just calculate. So you're going to see that the browser extension will flash green, and then it will grab the actual color that it's supposed to be showing. So red for the more carbon intense moments. So this is going to change according to the data that's brought back from response data carbon intensity. Almost done. Number 7, we're going to go ahead and look for 7, and we're going to update that icon. Where's 7? There it is. And here it's grabbing the closest color and telling the runtime in Chrome to go ahead and update that icon to the appropriate color. And those colors are sussed out and are set right here based on the value that comes back from the API. And the last thing you're going to do is you're going to navigate over to dist, background. And here's where you're going to go ahead and set that icon. So, because we're passing through to the background process, some image data, and it's going to draw the icon again according to the color that you want it to be using. And it's using the Canvas HTML API. So let's see if it worked. What we're going to do is we're going to go ahead and npm run build. This is going to kick off Webpack. It's going to build my extension. Okay, looking good. now at this point, I would go ahead and I probably for you, you haven't loaded this initially, so you load unpacked and grab this extension, but I can just reload it, and you see it goes back to a generic color. So here, it's back to where we were, and still we have these issues in New England. So I'm gonna call my senator. So that's what's going on. So that is your carbon trigger, that's your carbon extension. Now you have the knowledge to make decisions on when you want to run the dryer, when you want to go to the store to grab a couple of things from the grocery store, and perhaps when you want to run that machine learning model if your server is in your region. Or you can switch the region based on where your server is located. So that's another thing. Okay, so we refreshed our extension, we added our API key and region name, and congratulations, now you know when to run an errand or run your dryer. So as a recap, just remember that the greenest web asset is the slimmest one, the one with the least overhead and the one that's only called ad hoc. And you just built something slim that helps you build greener, and helps you make greener decisions. And you're an awesome web developer, and I thank you very much. You can always find me on Twitter at Jen Looper or on my blog at jenlooper.com. So thank you so much.
And you forgot to mention, we can also find you on TikTok now.
Yes.
Well, thank you, Jen. So we didn't have any question yet, but if you have time, I want to go on the chat on YouTube, because I know some people are watching the video with some delay, so they may have some question then. Okay,
Sure.
thank you very much.
Thank
We'll
you.
see everyone in a few minutes. Bye, Jen.
Bye.
I was on mute again, second time today. Sorry about that. So we are back, and our next speaker is Henrique Doro. I just want to say we have a little change. There's actually some construction works just by Henrique's place. So as we want to make sure that you can hear the talk properly and everything works just perfectly, we have actually a recording of Henrique's video. So we will play this recording, and Henrique is with us. And after his talk, if everything goes right, and if Henrique is able to answer to our questions, we will ask him the questions live. Otherwise, Henrique is going to come in the YouTube channel, and so he can reply to your question there. So, also, just a little anecdote, as we are used to saying anecdotes with the speakers. So Henrique told me that he eats sometimes some roots and some apple peelings. So that's really interesting for me because I'm not really used to doing this. So if Henrique can give us some tips later on what is good to eat, what tastes good for him, I would really like to know about that so I can eat this as well. And now we're going to launch the video.
Hey everyone. I'm going to share the tips on how we could build an eco-friendly web framework. My name is Henrique, and I'm trying to bring the web development to learning and getting over stuff. So please. Here I'm talking. We could go into many directions, but here I'm talking about a developer tool for building content-driven websites and web apps, focusing specifically on the front end. Okay, so we are not going to cover databases, permissions, complex APIs, high volume and highly complex apps such as Twitter, GitHub, etc. But instead, we're going to focus on the 95% of business cases out there, from marketing websites to admin dashboards and small social apps. And I know 95% is invented, but most websites need a way to generate HTML, CSS, and JavaScript. So that's where we come in with this framework. Our goal then is to conceive a developer tool that can materially reduce the carbon footprint of our websites and apps while still achieving economic goals and be inclusive and accessible. I only have 15 minutes, so I'm skipping context and most of the reasoning behind this. If you want more, then you can go into this URL that I left here. There I have a GitHub repo with a huge document that I went into detail into each of the things I'm going to propose. And also, I'm not going to measure things. I'm not going to talk about how do we know if it is materially reducing the carbon footprint. That's stuff for another place. 15 minutes is not enough for that. So it hurts my heart because I really wanted to cover those, but okay. So first, a rapid fire of features. We want to go through what we could build, ideas, directives, etc., to make this framework work, which is fine. But they're going to be very shallow. If you need more detail, go to this URL as well. Okay, so starting off, we want a hybrid operating mode. We would get the best from pre-rendered static content, the best from server-rendered dynamic content, and a little bit of client-side with a lot of caution where needed. And what do I mean by that? First, server-rendered server-rendered pages are great for dynamic content that is publicly available, because then we have up-to-date data that can be easily crawled by search engines. So that includes like leaderboards, social feeds, e-commerce, forums, stuff like that. But it has a problem. If you have low traffic, then most of the time your server is going to be idle. It's not going to be doing anything. So you're going to be using server and wasting energy for nothing. So if you have low traffic, this framework would allow you to go serverless. And serverless is a terrible, misleading name for something that basically means instead of you managing your own server, you let other people manage it. So we would not have a server running at all times. Every time we needed to render a page on the server, we would hit, I don't know, like Amazon, Google, Microsoft, IBM, whatever, asking them, hey, can you render this specific discrete function to get me the HTML for my leaderboard, for example. And then it would only run on demand. We could do some caching to allow it to, be reused. The same HTML be reused multiple times, and stuff like that. But then this way we avoid having to maintain a server at all times. A framework that is already doing this is Next.js, coupled with Vercel, their own platform, which is a great example. If you have the time, please look into their documentation. It's really interesting. So this is the idea, but of course, if you have high traffic, you're going to be requesting at all times, maybe serverless without their caching and complex routing and stuff like that. It's just going to be too much overhead, and it's going to add more friction and waste and use more energy than the actual server running at all times with you. And so you could choose both ways. Basically, the framework would guide you to either choose serverless or serverful based on your needs. Okay. Then for public content that doesn't change often, we would use pre-rendered / static content. So we would minimize server usage and increase performance, because assets would be ready to go whenever someone requested something. It would be just, the server would just grab those and send to the user without much time to be wasted. So we would save computations on the server, and we would also speed up the process of the user doing what they want, what they came for, which is very important. So the examples include like blog posts, marketing websites, documentation, which change every once, like a day maximum. Blog posts might, be there forever, and the author never comes back, which is very common. But we couldn't like rebuild the website every time a page changes. Otherwise, that would be very wasteful. Imagine like waiting, and especially if builds were slow. Like a build took 15 minutes, and you have a build like. Moza, you're on mute.
Again, yeah. Okay, thank you. So we are moving to plan C. Actually, we are going, as we heard that the sound was not very loud in the video on YouTube. We are going to try to do it live in the situation we are in. So that means we are not sure if the talk is going to break or if there's going to be some loud construction work here, but we'll try to make it work. Okay.
Sorry for this, everyone. I'll try to pick up from where I left. Yeah, okay. So, yeah, my connection is spotty because of the heat. So the energy has been crashing at all times today and yesterday. So that's why I'm scared. There's also construction work. But basically what I went through is just to go back, our goal is to create a developer tool that can reduce the carbon footprint of our websites and apps. The first thing that I'm proposing is that we have a hybrid operating mode that can do the pre-rendered static stuff that we see in static site generators, the server rendered that we are used to traditionally, like WordPress, Laravel, Express.js, as well as client-side rendering where needed, with a lot of caution, obviously. So the server rendered is ideal for when we have dynamic content. So it's very important that we offer that. And that goes for like leaderboards, social feeds, or e-commerce. But for most websites that don't have traffic, they 10 visitors in a whole day, then the server is running at all times, when it could be just what we call serverless, which is a horrible term for something that basically means it's gonna be running only on demand, only when we ask for it. And a good example of that is Next.js. I'm not going to get too much into that, and that's a bit confusing. That's fine. I have in the link here, I have some more details. Sorry for the time waste. And then the pre-rendered static content, that's where we can make the most gains in terms of server usage, to minimize it, to reduce the amount of energy we're using, and also to increase performance, improve UX. And we see that specifically fitting blog posts, marketing websites, and documentations, because for most of those, content only changes like at most once a day. A lot of times, the websites that we create for small businesses, they go in for like 3 months until they edit it again. And so if we have the static assets ready-made for it, that's perfect. We are saving a lot of energy to be used in the data centers and also the user device because it's going to load faster. But static sites have a problem where if you want to rebuild a page, you usually have to rebuild the whole thing, and that takes time and it is wasteful. So we would have to have fast and incremental builds to only rebuild the pages that change. I'm going to open YouTube on the side just to see if you are listening. Okay, so then the last piece of the puzzle is sometimes we have private content or small bits of interactivity that doesn't really need to go all into server-side rendering, which would drag a lot of energy and also can't be static rendered because it depends on the user and depends on the context, etc. And those includes like admin dashboards and CMS, and also complementary features such as comments. So we could render that with JavaScript on the browser in a way, of course, and before you think, oh, but JavaScript, it includes so much bloat, we would really be rigorous about auditing the file or auditing the JavaScript that developers are using, add lazy loading to prevent, for example, the comments. Most people don't even get to the comments in a post. We can load it only when they roll or scroll until then and then click on view comments, for example. This way we save some API requests, we save some JavaScript to be loaded, and then we save energy. Also, we could do only parts of the page to be dynamic, which is called partial hydration, and also let developers know that they could do better with frameworks that are more, they're tinier, such as Svelte, Vue.js, or Preact instead of React, stuff like that. Because like I put here, if we have the 700 kilobytes JavaScript behemoth, then we aren't doing our part, which is not what we want. Okay, so this is it. Like, this is the biggest technical thing that we can do in terms of educating and allowing developers to, on a per page basis, define what is the best strategy for them to serve that content, and then in a way that is going to minimize server usage as well as allow for all their business cases. But there are some other things we can do. For example, we could be based on JavaScript, which would really increase the reach of this tool because there are many developers that work with JavaScript. It's the biggest language and growing. And the bigger it gets, the framework gets, the more impact it makes. And also there is WebAssembly that we could use to import tools, packages, and code from other languages. We would be template engine agnostic. So if you want to like come from WordPress and you want to use the same PHP templates, we could figure out a way to do that to prevent a lot of friction in this whole moving. And if you're more productive with Nunjucks, you can use that, React, Svelte, whatever. And also be agnostic about data. So if instead of forcing every developer, every business based on this framework to use a specific set of things, such as, SQL database that has a specific type of post that is related to a specific type of author, we would allow them to pull data from wherever they want, including that, but also like pull from WordPress API, pull from Slack, GitHub, from headless CMS, from what have you. Then we want to make it as easy as possible to get into that, because if it's super complex and there's a lot of friction, people are not going to use it and we're not going to grow. And also it's a matter of accessibility. We don't want to be like a super complex tool that only the people who do computer science can use. So with 2 files, you're ready to go. But also if you want to go deep, you can for more advanced use cases. We would do a lot of front-end optimizations out of the box, mainly like dealing with images, like lazy loaded images, do aggressive compression, serving WebP and FF. I'm not going to go over the others. And also from the get-go, define a plugin system that allows you to extend this tool wherever you want to go, to provide a broad range of use cases. Again, for reach, we want to increase the impact. and also because it's going to allow people to be more productive. We would also guide developers to think about SEO from the get-go and also work on social displays of their pages in a way that on social media and on search, they can find the content and not waste too much time trying to find what they want. And also, you're going to convert more. So then the impact of your product is going to be bigger. And so your code creation is more effective. And that can go in a bunch of ways. Like we could have a schema generator. We could have a guided setup of how could you set meta tags in your HTML so then it's more SEO friendly. Ideas, there are many. You can take a look at this URL down here. I linked to a GitHub repo that I made where I go through all of these in a little more detail with more specific features. Okay, and then we also have like accessibility and internationalization. If we can't reach all potential users, we are failing our mission. So the idea is if we can guide developers and companies to build something that everyone's going to be able to use, by definition, we are increasing the impact that each product built with it can have. And also we are being more inclusive, and there's the whole nice warm morality of it, which is nice. And that could go into audits, could go into setting up the structure of your website so then you can have multiple languages in it, all sorts of features. We talked before about developer productivity many times. That's very important because each developer, if they spend a day worth of work to do something that could be done in 10 minutes, we are increasing the carbon footprint of the product because each developer has to eat and sleep and we fart as well. So it's important to be as productive as possible. And all sorts of tools like error handling and hot module reloading, like fast reloading while you're working on the website. That's all very important for this. We could do some design and business suggestions. That's pretty much our biggest leverage point. If we can avoid something to be built, that's best. Like Jen put before, the greenest app is the one that is not built. And the same goes for some features and some design whistles and bells that we use. So for example, we could in the terminal say, are you sure your organization needs to use Google Analytics? Maybe server logs are enough. You only care about how many people are hitting the website. And have you looked into more lighter weight alternatives such as Fathom Analytics? We could also be in the middle of the meeting and be like, hey, are you sure about this background video? Just imagine a robot voice talking about that. Like there are all sorts of these design principles or design patterns that we have that aren't user-friendly, and they aren't eco-friendly because nobody wants to see a video at the same time where it's spending a lot of bandwidth and energy just to show something that users don't want. So we could go into that direction. We could go even like to think, is this business model that you're proposing really important, like Uber for trading cards? What? So if we can prevent a business that is not going to have any traction to come up to life, then yes, we are doing perfect. That's, of course, it's hard, and I'm not proposing a specific implementation. That's just some ideas, okay? It's a dream list of features. And also we could do like an email, say, are you still developing this website? Is this still a good idea? In the last 6 months, even though you had no visitors, you emitted this amount of carbon. Maybe it's time for you to take it off the internet, which is something that Jen also raised before. And we would offer some actionable tips for sustainability in the docs, like a crash course on how to become a greener developer, offer a sustainable governance system from the get-go, because if the tool dies off, then the website will have to be rebuilt and won't be able to be maintained in the future. So if we want to be truly sustainable, the funding mechanisms and the political pressures have to be in place and thought of from the beginning. And this is like a bunch of ideas and possibilities that we could explore, but they are beautiful. But in the end, I don't think we need a new tool. What we need is education. no code is going to fix what we have. We can't be super, tech enthusiasts and thinking that it's just a matter of optimization and we're going to fix everything. It's a human problem. So if we don't take a step back to understand what are we doing that isn't sustainable, what can we do about this specific tool, feature, product that we want to launch, that could make it greener and better for the planet, better for the people, culture, and economy. So in the end, what I think, there are a lot of ideas here, but in the end, what I think is we should do is be more critical about our daily work, even as front-end developers. Yes, it's the tip of the iceberg in terms of impact, but it still is, there is significant impact there. And if I had more time, I would show some perspectives on the impact that this can have, materially, like numerically speaking. But that's the overall idea. If you feel like this is interesting and want to apply it to your own work, please reach out. I know I did it very fast. I was a bit nervous because it's my first conference and the video didn't work out very well. So, I'm almost shaking. Check out my link, reach out on Twitter, and if you want, let's chat about it. I really, really, really want to work on being a greener developer, and I think doing it as a community is going to be perfect. So that's it for me, Maud. I don't know, should we go for questions? Mute again.
Sorry, it's a running gag. I just wanted to say we don't have any question right now, but we have some very, very nice comments. Actually, someone said, "You're amazing."
Friends and family.
Yeah, I think everyone likes your talk, and great job on doing in spite of the conditions, which are special. And we're very happy that we had you for this talk.
Thank you for the opportunity.
Thank you. And so I will now move on to the little short break. And after a couple of minutes of break, we will come back with another speaker, and we will come Bill to join us. Thank you.
Hey, hello, Bill.
Hello, how's it going?
Great, great. Actually, it's only at the end of the day in France, so
I'm just getting going, so.
yeah. Where are you based? You're in the US, right?
Yeah, based just outside of Redmond, but in Washington.
Oh, okay, so it's the beginning of the day for you.
Yes.
Oh, feel sorry.
No, this is great. This has been, I woke up really early and have been able to watch all the presentations. This is really good.
Okay, so you woke up early to watch the presentation. Okay, because I heard that you're a big runner, so I thought maybe you went for a run this morning, but you stayed for the sessions.
Yeah, I can't run in the morning at all. My body doesn't work to do that. I have to do it at night.
Because you run, right? You do like marathons, like trails.
I do, yeah. I live kind of in the mountains in Washington here, and so it's really easy to just hop out my door and run around a bunch of the trails here in the mountains. I do mostly distance running, marathons, ultra marathons. I've gone beyond, but I like the long runs. It's a nice little meditational time for me to think about stuff away from everything.
Okay, you lost me when you said that mountains are just out of your door. So I'm so jealous. So I'll just let you do your talk and get you back after for the Q&A. Okay?
Okay, excellent. All right. Can we see it? All right, there we go. All right. So thank you, everyone. As you said, my name is Bill Johnson. I am a principal engineering manager at Azure SRE. SRE stands for Site Reliability Engineering. And for anyone that's not familiar with that discipline or that role, at a really high level, SREs essentially find engineering solutions to operational problems. And so some of the ways that we measure that work is through latency within a system, reducing the latency within it, the level of availability or how many errors there are and how much is acceptable for customers. If you hear the term of how many nines a service can support, that comes back to reliability, throughput of the system, and then also any saturation that can come in from data storage or bandwidth or anything. My role specifically is leading site reliability engagements, and those are temporary on the order of months or years of time, where me and a group of engineers go and embed ourselves with an Azure service. And our focus there is not about building new features. It's not about creating a bunch of new code and new stuff, functionality. It's about focusing just on the reliability aspects of the system. So those things I just listed off, the latency, the availability, the throughput, the saturation, and really trying to improve the reliability of the system itself. So I feel like I said reliability like 5 or 10 times there. What does that actually mean when we say reliability? At the end of the day, is the system there when you need it? Can you depend on it to be available, to be usable for a customer, for you as an engineer? If it's there, can you trust that it's going to do the thing that it's supposed to be doing? And then even more specifically, if it's there and it's doing what it's supposed to be doing, is it doing it in a way that is performant and is meeting the standards of your time? If a customer is expecting something to be ready or completed in milliseconds and it's taking minutes, that's a huge issue. And so that's where we come in and really focus on these reliability aspects of a system. Similarly, on the sustainability side, kind of when we say sustainability, what does that mean? Is this something that you can maintain over time? Is this a process or a power source or a set of code that is able to be maintained? Is it durable enough to withstand changes, to withstand outside influences or forces? And then can it adjust on the fly, or can it be tolerable to changing conditions? And so you don't have to completely rewrite something or completely redo something because one of the factors has changed. So traditionally, these two fields, so reliability and sustainability, these two concepts and fields have been very separate, and they don't really overlap as much. They kind of do a little bit. But at the end of the day, I feel very strongly, and my goal here is that sustainability and reliability are very similar. And in fact, sustainability sometimes can be defined as reliability over time. And as an SRE, our focus is really about creating reliable actions within a service over an extended period of time. One of the reasons we do engagements is that the goal is we should be able to go to a team in a limited amount of time, set up reliable systems and infrastructure and tools that can then exist without the presence of us. And then we can focus on another area of that system or another service or another part of Azure entirely. So really it's about reliable stuff, but sustained over a long period of time. So let's dive into a little bit of the sustainability side of this. I break this down into kind of three big areas of sustainability. And that first one is really about the technical components of a system. So what are the choices? What are the things that go into a system from a technical perspective that you need to maintain and be true over a long period of time? So, what types of CPUs or hardware or servers need to run in order to support your service in your system? What does that network look like? What types of programming languages do you choose? Is it a compiled language that needs to be built and it takes 6 hours to build it and deploy it? Or is it a scripting language that can be done on the fly? Or is it just basic HTML that you can not even have to upload and just save right there on the server? Those are all technical choices that we make, and each of those choices that we make in the system has some level of sustainability that's tied to it. The second level of this, from going from technical, is once you've made these choices, someone has to maintain these choices, right? Someone has to operate them. Someone has to push the buttons, and someone has to answer the calls when customers, submit cases and incidents. And so this operational level of sustainability is, what's the human toil? What's the human aspect of this system that goes into it that you need to maintain, or that whoever is in charge of the system needs to maintain? This is a lot of the stuff on the SRE side that we focus on as well. So, that on-call burden for an engineer that's going to get paged in potentially the middle of the night, do they have the right data in front of them, the right observability into a system to be able to make decisions for that system in order to save the customer experience so that customers aren't impacted as much as possible? How do you learn from those things going forward? It's not always just technical decisions. It's when something goes wrong, how do you break that problem down, learn from it, and apply those learnings forward so that those things don't happen again, or at least happen in a very different manner? So technical, operational, and then this third level of sustainability is probably one that we're all very familiar with here, is all of these things that we do from a technical and operational aspect have an impact on the environment, have an impact on our planet. We can measure these in any number of ways that have been touched on quite a bit today. So, PUE, carbon emissions, all scopes of those, carbon triggering, all these types of things fall into this environmental sustainability aspect of how are we impacting the planet based on our choices that we're making within the software. So these three areas, technical, operational, environmental, sustainability, they all exist and they all need to be operating in some balance. In the past, or traditionally maybe for software engineering, we focused very, very heavily on the technical. Can you just build a system that is now creating a thing for a customer to be able to do it? The Uber that was mentioned in the last time, Uber is a technical choice that was created to build and support the use case of someone needs a ride to get to somewhere, right? Those were all technical decisions that were made. And software engineers typically live and focus on that aspect. That's obviously not sustainable. And 5 or 6 years ago, Google introduced a new discipline called site reliability engineering because they found that the operational aspects of a system were far outweighing the technical ones. And so that's where SREs were essentially born, was to make the stuff that already exists work. Their goal is not to create new things, it's to make things that already exist that much better and easier to maintain so that we can then do even bigger and better things. And it's really that balance of technical and operational sustainability that SREs focus on. And so similarly, when we start to incorporate the environmental sustainability into this, that's where the sustainable software engineer comes in, is that balance across all three. You can't just focus on environmental pieces because the technical and the operational pieces will get unduly affected. Similarly to how the software engineer was traditionally thought of, is just focusing on the technical side. Conveniently, there's a concept we can borrow from economics and game theory called Pareto optimal, or Pareto optimality. And that Pareto optimal point is in a game is where no other player within the game can get more of a payoff without decreasing the payoff for another player. And so it's about finding that equilibrium. And that's really where that sustainable software engineer comes in as a balance, to find that equilibrium point of all three of these levels of sustainability so that everyone benefits equally. Not necessarily equally, but so everyone is at this nice equilibrium point to go forward. And that's essentially how SREs operate between the technical and the operational sustainability too. We can't go fully in on operational, we can't go fully in on technical. It's about finding that equilibrium, that balance point in between for the right level of availability or latency. And so at the end of the day, this is really just about the balance, right? There's a lot of things that come into play. There's business rules that need to be followed. There's compliance that comes in. There's government regulations. There's various customer behaviors that can drive and influence these things. And so that balance of these three areas is the key for sustainable software engineering. So what do we really mean about this? To go through a few kind of tangible examples here. At the end of the day, when we're talking about is really efficiency. If you can narrow it down into a single word or a single concept, it would be efficiency. It's, using the least amount of resources necessary to do the thing you need to do. So designing your software in a way that is the most efficient, setting up your architectures, that's a way that's the most efficient. You can measure these things through, PUE is something that's been mentioned already today. I know is just how much energy is being consumed for computing. That's typically used for data centers. But a good concept to think about is, traditionally people will deploy large services out into data centers on a rack of machines and whatnot. If you've ever been in the mobile app development space, it's a very different world. And so you're running off of a battery, and every choice that you make can drain the battery. Every choice that you make and how many times you need to pull the Wi-Fi for your location or something like that has negative effects on the customer experience by draining the battery. And so it's a good way to kind of reset the problem or rethink the problem. Is imagine you're developing this for a mobile phone. How would you do it differently? How would you use power more effectively? How can you approach that problem differently when you're constrained one of your resources? And then similarly, the compute utilization factor or CUF is another similar thing to PUE in that, but it's looking specifically at how well you're utilizing the compute that's available to you, and not necessarily the power. An interesting thing here is there's studies and data that's starting to come out now that's showing it's not necessarily 100% compute utilization. That's the goal, and it's really closer to probably that 70 or 80% where you want to stay. And that 70-80% is again going back to the balance of the benefit of getting that extra 5-10% of compute utilization is not offsetting the amount of processing power that you're getting from it, or the temperature that's being driven in there. And so again, to find that nice little balance point is the optimal place to be running your CPUs, typically around that 70 or 80%. So efficiency as a concept, what about on the hardware side? Roughly 75%, depending on the specific thing, but most servers and chips, CPU chips, roughly about 75% of carbon costs that go into it come from the manufacturer. They don't come from the operational or the lifetime of it. So extending the life of the hardware that already exists still has the largest impact today. And so how can you extend the life of the hardware? So just talking about the CUF is, if you're running your processes at a slightly lower utilization factor and not overclocking them all the time, they'll last longer. And so that's one way as well to extend the lifetime of the hardware. You can repurpose any older machines. You don't need the top of the line machines for things that aren't your critical workloads in your system, right? Taking these old machines and reusing them for testing and validation systems. You can create an entire test environment on, older or lower level machines that were at once your top of the line in production, but are now running there. You can set them up as an array of old machines for scaling up and scaling down, testing and validating those as your processes for scaling up and down, and where those trigger points are. And then one of my favorite ways is, old hardware is flaky, is going to be highly latent in some areas. And so use your old hardware as a chaos monkey at the end of the day. It's a really great way to inject failure into a system. It's a really great way to inject pressure into the system as take these things and build up just a chaos environment that's all the old machines, and you'll find some good fault injection scenarios over there too. What about the architectures of our system? So microservices, as just a real quick overview for anybody that's not familiar, there's kind of two architectural patterns of one is more of this monolithic where you kind of build everything and deploy it all as one single system out. And then there's another architectural pattern where you can break that down into smaller pieces and deploy each of them individually. In the monolithic side, you're going to deploy onto a single server, or probably have redundancy onto 2 or 3 servers. Whereas on a microservices architecture, you may have 10 services that all intermingle and connect to each other, which would then have to be redundant. And so you're running 20 or 30, much smaller, but more numbers of machines. As we talked about before, the number of machines is a big deal. And so in a microservices environment, which is a very common pattern today, how are you going to go about looking to find that balance? The easiest one that we've already talked about is the compute utilization. If you've got 30 cores that are running now, or 30 CPUs that are running, maximizing the utilization of those is very important and starting to grow and grow in the level of importance. Typically, each of these machines will have to connect to some sort of data store. And so optimizing that database is another critical component of this too. So if you're constantly scanning 1 billion rows on your request, can you add an index that reduces that to 10,000 or 100,000? Can you shard it across multiple different machines so that you're optimizing those requests and keeping those requests down? Don't need as much database storage space, don't need as much latency, so you don't need as much compute to process all of those rows. And then similarly, talking about latency is on the network side, optimizing that network traffic. When you have microservices now, you've got 10 different services that all need to connect to each other over different connectivity paths and latencies. Can you co-locate some of those and just put them on the same machine? Maybe they're in different containers, but all in the same machine. So it's all just local host traffic going back and forth instead of having to go out across the network and back. The good news is that across these 3 areas, you're essentially making your system more efficient, faster, and users will directly benefit from all these things. So not only are you increasing your environmental sustainability by reducing the emissions that are caused by your network and your database and the number of computes you have, you're also having your users benefit from a much faster and a much more efficient application that they're trying to use. And then, as always with microservices, you might just have too many. Like, do you really need that many microservices? If you have 2 systems or 2 services that are highly dependent or tight dependency on each other, just make them the same service. Do you really need to break those apart? It's again that balance where microservices are really easy to maintain from a developer standpoint, because when you make a change, I only need to update this one little thing, and the test cases and the permutations across them are much slower on unit testing or integration testing. And so when you make that more of a monolithic single system, it's a little bit harder to test, but the benefits that you see downstream from an environmental standpoint and carbon emissions can offset that benefit for the developer. So again, finding that balance point in between. And then specifically from architecture now into some coding operations, carbon triggering I know was touched on by Jen with the browser extension. Go install that she created. It's really cool. But this is a great concept where I won't touch on it too much. There's fluctuations in the various grids that exist around the world, power grids, and those are based on renewable energy. So when the sun isn't shining, or it's not windy, or maybe your drought and the hydro is a little bit lower, you'll have to offset that with dirtier electrical grids, the coals, the natural gases, the nuclears. And so these fluctuate over time as weather changes, as these things change around the world. So understanding where these fluctuations are and taking advantage of them in your software, making your software carbon aware so that it knows in a high intensity time, produce something else for the customer to do. Or you can take a proactive action on this by saying, shifting your workloads to greener regions entirely. If you run, just based on this graph here, if you run your workloads or your machines in Germany or Poland or the UK even, just shifting them to France or Norway or Sweden will save you carbon emissions and not having to change anything about your system apart from, latency. So, again, on that balance between business use cases and compliance and whatnot, if you have the ability to run your workloads in a different country, within Europe or anywhere around the world, that is something that's a very easy step that you don't have to change anything else just apart from where you deploy this, and automatically your carbon footprint and you're running these things in greener locations. So similarly, if you think of that as shifting your workloads in space, physical space or virtual space, it may be, you can also shift it in time as well. So can you delay any asynchronous jobs or batch jobs or anything like that that customers don't need immediate responses to? Can you delay those into times where there is a lower carbon intensity overall? So all these things can be built into the software components and pieces of the system. But overall, I think I'm now the third, maybe fourth person in a row to say this, that the greenest system is one that is never built. There's a very similar operation or component here from the operational side where, you know, the easiest system to operate is one that's never built. But those aren't realistic. We still have things, we still have systems that are built. And so finding that balance is really the key, right? And so again, can't go all in on environmental because there's still functions, there's still things that need to exist for people to use and take advantage of. So finding that balance between all three layers of these sustainabilities is the key, and is where you see the most impact across, and where people want to jump in and are able to use these systems and take advantage of them in the first place. And then I'll just do a quick pitch here for the principles.green as well. If you haven't seen this, or I think Asim mentioned it at the start here, please go, if nothing else, start the conversation with the rest of your group, with the rest of your teams. Become a contributor as well on this. It's on GitHub, pull it, make your changes, submit the concepts that you have, help and contribute here. But mostly think about how all of these apply to your system and where your trade-offs are and where you can take advantage of some of these things. That's really, at the end of the day, what we need to start instilling in everybody is making sure that those questions are asked. We may not like the answers today, but ask the questions, and those answers can start to evolve and change over time. And that's it. I don't know if we have time for questions, but feel free to reach out to me at any of these spots or locations.
I think we're running out of time for questions, unfortunately, but if you can go on the chat on YouTube and just check at people if some people ask for questions. We'll wrap it up because we have just 1 minute left. So I want to thank everyone for joining us. Thanks to all the speakers and all the partners and all the people who had this conference to happen today. And that's it. Thank you. We'll see you for the next conference. Bye, everyone.
Dankeschön.
Merci beaucoup.
Muchas gracias.
Merci d'avoir été là et on se voit la prochaine.
Thank you, El.
Mulțumim.
Merci beaucoup.
Dziękuję.
Thank you.
Obrigado.
Salut.
Bye.
Ouais.